Okay, so it says that the purpose of edge detection is to find where brightness jumps occur and then to mark those, right? So for example, if you consider a picture like this, then ultimately we want its output to be like this, okay? That's what you want. So to repeat, the purpose is to find brightness jumps. And so before we get into detail, we're going to introduce the concept of convolution. I want to make sure that you understand this is the historical notion of convolution, not the convolution that people use today in CNNs, meaning CNNs come out of this idea, but you first need to understand this basic idea, right? So the basic idea is that convolution is an operation between two tables, okay, normally between an image, possibly on the left. They typically write the bigger table of numbers on the left and the smaller table of numbers on the right, okay? But it doesn't have to be that way. And the convolution operator is that asterisk with the circle around it, right? So that's the traditional way to talk about convolution. And so you want to know what is the output of that convolution, right? So somebody has this problem for you. They say, these two tables, please do the convolution, give us the output. So the way that you do it is you're supposed to do all of these carefully done steps. And this is from the mathematical definition of convolution, okay? Not what CNNs do today, but the mathematical definition. But the mathematical definition is you first pad the left array with an ocean of zeros, as I say, okay? Then the second table, you double flip it, or you do a diagonal flip, and then you compute the weighted sum, okay? And I'm saying a whole bunch of things. In practice, we don't do this and that. In practice, we don't do most of this. In practice, we only really compute the weighted sum. But let me walk through the steps carefully so that you're not missing anything. So this was the table on the left, okay? So it said pad it with an ocean of zeros, right? So I put it in the middle of an ocean of zeros. I have zeros everywhere going on to plus infinity, minus infinity, up, down, everywhere. There's infinite ocean of zeros, okay? That's what you're supposed to have. Then on the second table, this was my second table, it says I'm supposed to do a double flip on it. So double flip means this is my first flip, and this is my second flip. Do you see how I just first flipped along the X and then I flipped along the Y or something, right? And that ended up with like a diagonal flipping thing, okay? So that's the formal definition of convolution, the second step. Then the third step is you're supposed to compute the weighted sum, okay? And hopefully by now you've seen enough of this in Dr. Shah's and other notions of convolution and so on to know that what you're doing is, so you know what a sum is in mathematics. A sum is that sigma notation, right? The big capital E looking thing, the Greek symbol sigma, right? That's a summation symbol. That's what is known as the summation, basically. When you're summating a whole bunch of things, or when you're summing them up, you're simply adding them up, right? Now, a weighted sum means you weight, you W-E-I-G-H-T, you put a weight in front of every number before you compute the sum, okay? And so you're taking a weighted sum of the second table. So the second table is seen as the weights, the W-E-I-G-H-T-S, the weights. And the first table is the table that you're applying that set of weights to. And then you're going to add up the weighted sum and get a number back, okay? So in this case, it turns out the simple number is only 42 because only the 1 matches up with the 42 in the green box. And the zeros all cancel the rest of it out, right? Okay, so I hope those are fairly basic concepts for you. So now we go back to our own problem. So we start doing the same weighted sum thing, but now we have to scan the smaller table top to bottom, left to right with respect to the bigger table. But the bigger table, now remember, we put it in an ocean of zeros, right? So that is the ocean of zeros there. Of course, I'm not starting at the real extreme end of the ocean. The real upper left extreme end of the ocean would be far away, and we'd be doing it and we'd be doing it and we'd be doing it forever until we finally came to where the action is in these 4 numbers that were there. But of course, along the way, because we're doing a weighted sum, we'd just be getting 0 and 0 and 0, right? I hope that concept is very clear to you, why that's the case. So we can short circuit that ocean of zeros and just go to the boundary of the island, right? So if you imagine the original table of numbers is a little island and I've got the ocean around it, I can just go to a few waves around it and start there, okay? So that's what I'm doing. So I took my little smaller table. The smaller table is the one I double flipped, right? So I double flipped it and I take the weighted sum. And of course, again, because the ocean of zeros is still an ocean of zeros, I get an answer 0 in there, okay? So that's what I get there. So that's what I call, in my own definition terminology, I call that an example of a one location convolution. That is, I just did a single summation and got it done, okay? Now, if you move the location of that smaller table, if you scan it along to the next set of possible numbers and the next set of possible, then that's what I will call a scanning convolution. And again, when people use the word convolution these days loosely, they sometimes mean both, Okay, so you need to be very careful. Are they talking about the single step convolution where you only get one number out of that calculation? Or are you scanning it along to get a table of numbers out, right? And again, I hope that's clear to the beginners as well, what I'm talking about. Hey, by the way, let me just ask you to identify again, who are the people that have had zero background in either religion or machine learning class? You've had zero of it. And in fact, you're maybe a beginning CS major, you know, you've just done a few classes in CS. Can I just get each of you to say your name loudly so that I know that that's who I'm mostly talking to this morning, right? Okay, I want to make sure that you guys are completely paying attention. I don't want to lose any of you. I don't want you to be lost in what the heck did he do type thing, meaning my presentation is supposed to be basic enough. And I'm also supposedly, you know, an excellent teacher at this kind of material. So I want to make sure that I'm doing my job, right? Okay, so can I just ask those of you that are the beginners to just say your name clearly for me? Please go ahead.
Jenna.
Audrey.
Callie.
Pedro.
Okay, Pedro, good. I have 4 names so far. Who else? Okay, so the rest of you believe you have seen some of this material before in your life somewhere, right? And that's okay, okay? So Kaylee, Jenna, Audrey, and Pedro, did you understand whatever I've said so far?
Yes.
Yes.
Yeah.
Yes.
Okay, so now the next slides then continue to show the scanning convolution, which is, notice that the 4 arrowheads at the top of the figure have moved to the right by one set of numbers, right? Do you see that? So I kind of scanned along, okay? I moved it. It originally was at the upper left, right? And I got a 0 answer there. Now I've moved it 1 more over to the right. And again, I'm going to do that. And just by amazing coincidence, again, the answer is 0 because, of course, I'm just looking at a bunch of zeros in the ocean there, right? Okay. So that, and at the bottom of the slide, I'm recording my answer as I'm going along, right? So I had a 0 from the previous one that was in the upper left answer, right? That's the first 0 I got. Now I got a second 0, right? I hope you're following all that carefully. Okay. So now I'm randomly going to move it along. Okay, meaning, of course, I will have done the others very carefully, but I'm kind of skipping along a little bit. So now I'm skipping to the new position where I have a +2 and a 0 and a 0 and a 0. Do you see that? And again, I do the weighted sum of that whole thing, and I get a 6 from that. Do you see how I got the 6, guys, particularly the 4 that I'm focusing on?
Yeah.
Yeah.
Yes.
Okay, so you see how I got the 6, right? So that's that. Then I could have gone and done this more carefully for everything carefully, and then I would get this final answer at the bottom. And of course, what I've done is, where it says the weighted sums, what I've done is I have hidden the boundary of it that was a bunch of zeros, because again, we really only care about when the action begins, right? And you know that the action only begins. As I'm scanning along my small table and I'm scanning along the bigger table, I'm going through a bunch of ocean of 0, 0, 0, 0. I don't care what I get because I know I'm getting 0. So I really only care when I start hitting the little island that I care about, right? Okay. And so that's why I get this final answer. And again, I recommend that those of you who have never done this before, that you go through this example carefully. I do recommend that you do it, at least a little bit of the numbers, go through it carefully and verify that you get the same numbers that this answer table says, right? Okay. So I'm going to move along. Okay, so now that we've defined the notion of convolution and how to execute it, right? So from now on, we can just blindly say we want to do a convolution, and you should know what we're going to do. Now, the only thing I want to say to you is that we will not be doing either the ocean of zeros or the double flipping, okay? And in practice, when you get to the actual neural networks, the ones that are practical that we're going to be using for the rest of the summer, there will be a notion of something called padding, okay? Padding, P-A-D-D-I-N-G, right? And that padding is about putting the ocean of zeros, okay? So just keep that little note in your mind that padding is basically that. It's how much of the ocean do you use or not? Do you pad by only, you know, a couple of rows and columns of zeros, or do you pad by, again, 10 columns of rows and zeros or not? Okay, so that's what the notion of padding is. And as you're moving your convolution, your smaller table around, that notion in the advanced convolution neural networks is going to be called stride, S-T-R-I-D-E. That is, how much do we move our table by? And do we just move it by 1 at a time, or do we skip some and move it by 5 at a time, and so on, okay? So all those notions will become clearer the rest of the day. But for now, we're going to go back to our question of edge detection. Okay. So we've done that, and so now we go back to edge detection. And so again, this was the picture that we want to find the edges for. And so now we will say, imagine we took a row of such numbers from that table of the picture that we just had, the picture with the chess images. Take a row of numbers. So, and that row should pass through one of the chess pieces, right? So then the row might look something like 1 and 2 and 1 and 0. Now that's because those numbers are the black ones, right? If I go back a slide, see how I have a black background, and then I have some white chess piece, right? But I'm going across a row. I'm taking a row out of this picture. So I took the row out, and I'm scanning along. And so I start out seeing black first, and then eventually I see white, right? So that means I'm scanning along. I see some very tiny numbers because black means tiny numbers on the in the picture. Then I jump to numbers that look like 99, 98, 100, okay, closer to 100 because those are the white pixels, right? And then I drop down again to dark numbers again because I finished that chess piece, okay? So do you all understand where this row of numbers came from and all that? Particularly the four students?
Yes.
Yes.
Yeah.
Okay, okay. And so then I can look at the absolute value in the jumps, right? So as I'm going along, I went from the 1 to the 2, from the 2 I went down to a 1, from the 1 I went down to a 0, then from the 0 I went to a 98. So I'm going to be recording the absolute value of my jumps in the values, okay? Because that's what finding an edge means, right? I want to find the jumps in the brightness, right? So I'm recording that, and then I'm plotting down below in the red plot, I'm showing you where those jumps are, where the jumps are large, right? Okay, so earlier on the jumps are very small because they're +1, -1, and so on. Then they become large, almost 98 and so on. And because I've taken absolute value, I flipped the negative values to the positive side, okay? So that was what that was. So now I can go ahead and write a simple algorithm for edge detection, right? So I can say, create an algorithm in pseudocode. While my row is not ended, I'm going to keep on going down by pairs of numbers. I'm going to select the next AB pair. AB is the pair of numbers for whom I want to consider the jump, right? I want to figure out what their jump in values is. So I keep going AB, AB, AB at a time, each AB pair. Along the way, for each pair, I stop and I compute the difference value. DIFF equals B minus A, right? Because that's what a difference is, right? I'm going along and I'm computing the difference. Okay, then I ask if the absolute of the difference, if the absolute value of the difference is greater than some threshold, okay? The reason I need a threshold is because some of those jumps were +1, -1s, right? I'm not interested in those kinds of jumps. Those are too small jumps. Those are just noise level of jumps. So I'm not interested in those. I'm interested in the big jumps, right? The jumps that were like closer to 98 or whatever. So I'll pick some threshold, and the threshold could be 20 or 30 or whatever. And if the absolute value of the difference was greater than the threshold, I'll mark that as an edge. Okay, so far, is that all clear? This is a basic first attempt algorithm at edge detection. Anybody could code this up, right? Okay, do you guys all see that you could have programmed this up yourselves?
Yes.
Yes.
Very good. Okay, so I'm going to move on.
Yeah.
So now the next difficult concept, this is the real jump in intellectual work, is to understand that that step of diff equals B minus A is the same as a one-step convolution, as a one-location convolution between the values of the pixels, that was A and B. So A and B were in my picture, right? Those are the values in the picture, convolved with a -1 and a +1, okay? So I've got this yellow box now that I brought out of somewhere. I just made it up, right? I said, hey, I'm going to be really cute, and I'm going to create this yellow box, and it's going to have these two values in it, -1 and +1. And then all I'm going to compute to get the differences, I'm going to do the one location convolution between the AB and my yellow box, okay? And that's the same as B minus A. Can you all convince yourself of that the one location convolution is that? Without doing the double flip and without doing the ocean of zeros and all that. The simple weighted sum is that, right?
Yep.
Yes.
Okay, so is that all clear? Okay, very good. So now I have brought in the notion of convolution into my previously very simplistic algorithm that I had, right? I had a very simple pseudocode algorithm that computed the difference. But now I've replaced that B minus A line, I've replaced it by this convolution step, right? So you see that? Okay. And so now I'm going to be basically reading in my image. My full image is the brown values A and B. I'm going to be reading in them one pair at a time. And then I'm going to do this convolution with the yellow box. And then I will ask for the absolute value greater than threshold. And if it is, I'll mark it as an edge, right? Okay. And that'll be my way of processing through the rows, right? As I go through row by row, okay? Because that's the only thing I've done so far is row by row. So then that's a scanning convolution because I'm moving the A and B around step by step, right? That's not a one location, meaning I'm doing the one location convolution within the loop, but overall the loop is executing the scanning convolution for me, okay? So is that all clear so far?
Yes.
Yeah.
Okay, I'm moving on. Okay, so now the next concept is that I need to be worried that I've only done the X direction, right? The horizontal direction, the rows. I haven't done the edges around the columns, right? So I'll very simply go ahead and do a similar pair of yellow values, but they're now moving vertically. And I have a -1 +1 then in that direction, in the vertical direction. And I will simultaneously then, as I'm doing the horizontal scanning, I will do a vertical scanning of this new yellow pair that I have, right? And so now the point, so first of all, is that clear what I'm just saying? I'm going to be doing the X direction and the Y direction, right? At the same time,
Yeah.
okay?
Yes.
Okay, so now the point is that I will get back two values. I'll get a value for the X convolution that I just did, and I'll get a value for the Y convolution I just did at every location in the image, right? So now the fact that I get two values, that constitutes what in math they call a vector, right? A vector is basically a list of values, okay? Now, a vector, when we think of a vector in distance and so on, in direction and so on, then a vector tells us which direction to go in on the planar XY plane, right? Or I could have a 3D vector if I'm traveling in 3D space, then I'd have three different parts to that vector, an X, Y, and a Z that would move along that way. But that notion of vector is from dynamics and motion and so on. The basic notion of vector is just anytime I have multiple values for something, I have a vector, okay? So now, in our case, my multiple values are the horizontal answer and the vertical answer, right? You all clear on what I mean by that? The one that I got from the X convolution direction and the one that I got from the Y convolution direction, right? Those are the two members of my vector. And before, when I was simply dealing with the horizontal only, I simply said if the absolute value that I got back was greater than some threshold, right? Well, now the problem is that I have two values. So how do I deal with the both of them at the same time, right? How do I have a notion of absolute value, of magnitude, of size of that jump when I have two values to compare? Well, again, math is wonderful and beautiful. And math says, because this is a vector, the pair of numbers can be represented as a magnitude. So the magnitude of a vector you all remember from your basic vector calculus or somewhere else, maybe pre-algebra or something like that, you did this. You take the magnitude of a vector by taking the X component and squaring it. You take the Y component and you square it, you add them both up, and then you take the square root, right? So this is like the distance formula, right? The distance formula that you did in middle school. It's the same as magnitude of a vector, okay? And sometimes this is called the Euclidean distance or the Euclidean magnitude of a vector. Sometimes it's called the L2 norm. These are all the same words, okay? L2 norm, Euclidean magnitude. These are all the same ideas because there are some other ways to ask about the size of a vector. There's the L1 size of a vector. This is L2, I told you, right? This Euclidean distance thing with the square root of squares. There's a way to ask for the L1 size of a vector, and the L1 simply takes the magnitude of the X component and adds it to the magnitude of the Y component, adds it to the magnitude of the Z component, adds it to the magnitude. So you just add up the simple magnitudes. You don't square them and square root them. You simply add them up and you add them up, and that's your L1. And I should just quickly tell you the L1 versus L2 notions. They have to do with if you're in a city, right? And let's say you're in Manhattan in a grid, right? And you cannot travel diagonally from the northwest corner of the city to the southeast corner. You can't just fly like the crow could fly. Like a bird could fly diagonally, right? Shortest distance. But you have to do step by step. You have to go one left, then one right, one down, then one side, one down. You know, so you're going stepwise, right? Like in a staircase kind of manner. You're going traveling through Manhattan on a grid. That is basically the L1 distance. When you're traveling city blocks to get from one corner of the city to another corner of the city, when you're going through by city blocks, That means you're adding up the full number of X components and the full number of Y components, and you're adding them up, and that's how much you have to travel. So that's the L1 distance, okay? The L2 is the crow flying shortest distance, the Pythagorean theorem, right? Okay, so that's that, okay? So far so good, guys. You understand how I got the magnitude of a vector? And so now I can go back to my algorithm, my wonderful edge detection algorithm. I'm trying to get to that algorithm step. So I'm just scanning ahead in my slides here. Okay, so now this would be what the actual algorithm would look like, right? I would have done my convolution with the X set of yellow values, and I would have done my convolution with the Y set of yellow values, and I would have stored the outputs. The output for the X set, I would store an outpick X, and the output for the Y set, I would store an outpick Y, right? So now I would simply go through and calculate the magnitude of those values. And so I'm taking the square root of the outpick X times outpick X, that is basically outpick X squared, plus outpick Y times outpick Y, which is basically outpick Y squared, right? And so now I get that I val represents for me the magnitude, okay? Don't worry about why I'm doing those last two lines there. If I val greater than max I val, just ignore those lines for now. But you understood how I would have calculated the magnitude, right? Okay. So now I can go ahead and I can back up a moment to show you. I'm backing up in my slides here. Okay, so this is where we were, right? So the next concept is that those +1, -1 values that I took, those are basically called the discrete approximation to the continuous derivative, okay? And I take it some of you have just taken calculus recently, right? Like in the last 1 or 2 years, you've taken calculus. So if you recall, in calculus, the very first chapter of the book, normally the way it proceeds is they don't immediately jump into d by dx and all that. They first start telling you about, they give you a table of numbers, and a single array of numbers, a single vector of numbers, and the numbers might be the temperatures in the city across every hour, right? Or it may be the population in the US across each year, right? And so they give you this list of numbers, and they tell us when the temperature either jumped the most, or when the population jumped the most, or when it went down the most, or whatever, right? And you're supposed to take differences between pairs of numbers, right, to get that answer. That's the same thing that we just did, right? We convolved with +1, -1. That's the same as going through the list of temperatures in a city or the list of population growth in a city, in a country, and asking when is the jump the most. And that's normally how a calculus textbook starts in the first chapter, okay? They do that basic difference between two values so that you understand that you're looking for the rate of change, right? Okay, but really, realistically, what that all is simply the mathematical derivative. So it looks like this. Normally, you're very comfortable with the notion of taking di by dx, right? Or df by dx. You've done that a million times in Calc 1. So the only big change here is that because your function I, which is your image, is a function of x and y, right? It's not a single vector of numbers, but it's not a single list of numbers. It's not a single row of values or a single column of values, but it's a table in the x and y direction, right? So it's a function over two variables, x and y. So then when you ask for the derivative in one of those directions, you call it the partial derivative, okay? And that partial derivative is indicated by that symbol, little delta. So it's partial, or sometimes it's called the partial. So it's the partial of I with respect to the partial of x. And then at the same time, you have to compute the partial of I with respect to the partial of y. So those are your two derivatives in the two independent directions, right? And again, I don't know how many of you have seen partial derivatives yet in your calculus classes or not, but the concept is very simple, okay? Don't let it scare you away. When I took that material in calculus, I was all scared away because I thought this notation looked really strange to me and all that. But then I realized after studying vision that it's really very simple. You're just saying, what is the derivative in the x direction? What is the derivative in the y direction? Okay, that's all it is. And so you've taken those two values at the same time, and so they constitute your new vector now of derivatives, and then you're going to ask for the magnitude of that by simply taking the square root of the squares, right? Okay, so we all good with that so far, guys?
Yes.
Yes.
Okay,
Great.
good. Okay, so I'm going to move on now. So now this is just showing you the absolute value of the differences in one direction only. And so then the next idea is that you want to have a threshold, right? You want to have a threshold. So the threshold is like the water level in the ocean, in the real ocean, the water level. Like I always find it very interesting. I don't know, those of you who don't live in Florida, you may not know this, but there's something at the end of Florida, the southest end of Florida, which is called the Keys. Okay, and the Keys are a bunch of little row of islands that you can hop across because there's little bridges joining them and so on, and they run, right? They run through the ocean like that, and so it's it's a big tourist sort of place because it's like a unique place where you have water on both sides of you, right? But it's a long strip of island, right? Well, what's very interesting is that if the water level, if there ever was to be the reverse of global warming and there was supposed to be global cooling, which can happen at any time because you never know, these things seem to be a little bit rare, and even though no one really knows, but the point is there could be global cooling someday, right? And many times there was global cooling, and when that happened, all the water in the oceans go to the poles, the ice caps, and so what happens to around Florida is that you would literally be able to walk along that ridge. You'd never need to cross any bridges, right? Do you all understand that basic concept that I'm trying to get across?
Yes.
Because the water level would drop, more of the land is visible, right? Someday if the water level rises, let's say it rises by 10 feet or 20 feet or something like that, supposing it did, okay, I don't know that it can, I don't know that there's enough water on the planet to rise by 20 feet, but supposing it did, then most of Florida would be covered, right? So similarly, you raise your threshold high or low, you're going to be raising your, if this is the ridgy output that you get from running that magnitude calculation that we just finished, right? This is a ridgy output. Why is it ridge-like? This is not the edge detected. This is not the final edges. This is the ridge image that you get from running the magnitude calculation, right? So if you were to zoom up on this, it would literally look like a bunch of mountain ridges, each ridge near the border of each object, right? Okay. So what that means is that you're starting from, let's say, the left, and you're traversing this ridge image, and you would be, initially it's all black and flat. Then you would begin to see a ridge. Then you would climb up the ridge. Then you would be done with the ridge, and you'd be now climbing down into the center part of the object, the center part of the piece of chess, right? Either a pawn or a rook or whatever this piece is. The center part is again dark. And then you encounter the right boundary of that object. And there's another ridge there. Do you all understand what I mean by ridges and all that?
Yes.
Yes.
Yeah.
Okay, so that's what I really have, okay? I have a ridge-like image, right? A ridge-like output, right? From the magnitude calculation. So I'm gonna now apply the water level thresholding. So this is a very low water level, okay? I lowered my water level low enough so that I can see most of the things above the ridge, and I've turned them into white pixels, okay? Alternatively, I could have been very strict on I could have raised the water level, and I could have said I only want edges that are very strong edges, right? At that point, I tend to lose the horse's head, okay? Because the horse's head, if you back up, you'll see that the horse's head, the jump from the background to the horse's head was very faint. Do you all see that?
Yes.
So it's a weak edge there, right? It's a weak low edge, not a strong edge like the other parts of the chess pieces. So that's why I get a low ridge, and I lose it when my threshold is too high, okay? Okay, basically I'm done though with what I wanted to do for convolution. Do you all feel you have a solid understanding of convolution and how it gets used in edge detection?
Yeah.
Yes.
Yeah.
Okay,
Yes.
and you understood how you combine the two convolution results, you combine them with the square rooting and squares and all just to get the magnitude, right? Now, I want you to understand this is historical information. So this is 1964, 1965. when the notion of convolution is already there in math, right? And they write up this edge detection operation. And this is the one I just covered for you is called the Roberts operator, okay? Roberts operator simply just takes the derivatives, and that's all we've done so far. Now, what I will do next for a few minutes is I'll talk about a new problem, which is that your chess piece that you're going from the left across the middle and then to the right, your chess piece's profile of brightness is not nice and smooth like the blue curve. It's not like the blue curve. It is like the red curve. It's jagged and it's got little noisy points in it. Where does the noise actually come from? Do you have a basic idea?
Is it compression?
Well, so the noise can come from a million different places, right? Including compression, okay? The classic thing of noise, whether you compress or not, the classic reason for noise is that the actual digital recorder itself is not perfect, right? It's a sensor and it's averaging light. It's averaging the light that the photoreceptor gets. It's averaging it over a period of time. And so that averaging, maybe the light itself is flickering and so on. So the measurement itself is not perfect, okay? Sometimes it's averaging. The true image out there in the world is a boundary between a black and a white region of image. Like maybe you're looking at a piece of text or something like that, and there's a black print on the white background in the text. And that pixel that the camera is capturing that moment is right centered on that boundary, right? So it's averaging a black and a white region, and the averaging sometimes may seem more black, sometimes may seem more white, so it flickers, and that flickering is what leads to noise, okay? So the bottom line is that the main thing we need to know is that we don't have smooth inputs that are perfectly representing what the true image is. We have this noisy thing and all. So what we want to do then is we want to lead to a smoothened version first, okay? So we want to lead to a smoothened version. And the best way to smoothen things out in life is to be like a communist, right? And so communists say, take a whole region of neighborhood, all the houses in there, and we are going to average their wealth, right? So we don't care whether one is a rich person, did whatever they did, and the other person's poor. We're going to average it out. We want all of them to have the same wealth at the end of the day. So what do we do when we average? We simply take our values. If you got four neighbors, 4 houses neighboring that you're looking at, a block of 4 houses, you're simply going to multiply each by a quarter, and that's going to be the average, right? Or that's the same as adding up the 4 values first and then dividing by 4, right? Okay. So what you need to understand is that where this is important for us is to notice that an averaging process is the same as running a convolution on the image with a small table of 4 quarter values. I'll let that sink in for a while. Make sure you really understand that point, okay? That if I have a picture with 4 pixels in it, A, B, C, D, then I want to smoothen it out, right? So I want to take the average. Then that average calculation is the same as convolving the overall picture with these 4 1/4 values. Are you all convinced that that's the same as taking an average?
Yes.
Right, because I'm weighting, W-E-I-G-H-T-ing, each of my A, B, C, D values with a quarter in front of them, right? And then I'm going to add them up. That's the same as adding up A plus B plus C plus D and dividing by 4, okay? So that's how I got my averaging going on. So this is going to be what I'm going to apply now. I'm going to first convolve my image with an averager first. The averager is going to smoothen things out. So what I'm showing you is that just look at the bottom set of numbers, okay? So I have the image in the block in the brackets, right? And I'm convolving the image with a set of 4 ones. Those 4 ones, I have pulled out the common 1/4 to the left. Do you all see that common 1/4 I pulled out to the left of the parens?
Yes.
Yes.
Okay, those 4 ones were not 4 ones at first. That quarter value that I pulled out to the front, I should have put those 4 quarters in each of those 1 positions. Do you understand that? That's what I really meant to do, right? But that's the same mathematically as pulling out the common 1/4 value at the front and just leaving the ones in there. You see that?
Mm-hmm.
That's because it's a common value, right? It's a quarter, quarter, quarter. So I can pull out that quarter at the front, right? And what I'm left with is just ones after I pull out the quarters. So that means that I can simply now conduct my smoothening part of the operation by taking my image and convolving it with 4 ones, okay? And then finally remembering to divide the whole image by a quarter, right?
Yes.
That will have smoothened my image out for me, okay? Now, then I still want to do the second convolution, which is the derivative convolution, right? The -1 + 1. Initially, my -1 + 1, 2 yellow values were just 2 values only, right? Now we've doubled up on it. We put the 2 values on the top and the 2 values on the bottom as well, the same values. So basically, we got a square table, okay? And the only reason they did this was because back then in 1964-65, they had very, very small amounts of memory for writing programs. So they wanted to reuse the same code that was used for the x derivative and the same code that was used for the y derivative, right? But the only way to do that is to make the shapes of the tables the same, right? Because otherwise you have a different size table. You have a 2x1, a vertical table for the y and a 1x2, a horizontal table for the x. So you need different kinds of program for that, right? So they wanted to reuse the same program. So they said, well, let's just square the stupid thing up so that we can reuse the code. And so now our calculation looks like I've got the quarter at the front, the image convolved with the 4 ones and then convolved with the +1 - 1s. And so another step I can do now is, because convolution is associative, meaning convolution is like multiplication. In normal numbers, I just multiply them out, right? And I have a chain of multiplications going on maybe. When I have a chain of multiplications, I can use the associative property to do whichever subparts I want first. Convolution is the equivalent of multiplication on large tables of numbers. Okay. So because of that, the associative property of math applies again. So I can move my parentheses over to the right pair first, and I can do those first, okay? Now, if I do those first, where were the rules for you to know how to finish that right pair of convolution that I have going on? Where did I tell you the rules for how to finish, execute that, and do it? Hello? Hello?
What do you mean when you say, where did I tell you the rules?
Well, first of all, you understand I've given you a new problem there on the right-hand side of that long line, right? I've just told you, please convolve for me a table of 4 ones and another table of -1 + 1 -1 + 1, right? Please convolve for me and give me that answer. I want to know what that answer is, right? How would you know to finish that little step that I've asked you to do?
Would you pad one of them with zeros and then do the row by row product sums?
Very good. That's exactly the answer I was looking for. I told you that rule in my very first 2 slides, right?
Mm-hmm.
The rule for a simple 2x2 table, if I have 2 pairs of 2x2 tables, I told you what you have to do. You have to pad the left-hand array with ocean of zeros. You do a double flip on the right-hand array, and then you do the scanning convolution along, and you get your final answer, right? Okay, so that's the correct answer. Oh, by the way, who was it who answered my question?
Pedro.
Very good, Pedro. Okay, so you're keeping up, and that's good, right? As a new person, okay? So that's the point, that you can do this convolution. You can actually do this yourself now, right? Meaning you don't need me to finish it for you. But it turns out, I will show you how it's finished. So now we're going to be getting rid of the 1/4 in the whole system, because the 1/4 is just like a final afterthought, right? Like we got the final convolution answer of everything. And then we realize, oh my gosh, we got to go and multiply everything by a quarter, right? But that's the same as saying, I'm going to be using a threshold anyway later on. So if I'm going to use a threshold, then why do I need to keep track of my quarter? I'll just factor that quarter into my threshold. So it's like grade inflation, right? If everybody's getting hundreds on the exam, the professor still can't give out A's to everybody. So the professor has to multiply, scale up that thresholding difference between who's an A and a B. If on the other hand, the exam was very hard and everybody got a 40% on the exam, then the professor can scale up the thresholds, right? Can scale it up, can double up and say, okay, who was a 40 is now going to be an 80 and so on. So that's just applying a scale factor, right? So I just want you to know that I can forget the quarter at the beginning, because that quarter, I will take it into account when I do my thresholding later on. Because at the end, I have to apply a threshold anyway, right? My thresholds are arbitrary. Some boss decides what's a reasonable threshold or not. So whatever threshold the boss told me, I'll say, hey, I forgot to divide everything by a quarter, to multiply everything by a quarter. So I'm just going to go and factor that into my thresholding later on. And therefore, I will multiply my threshold by 4. Okay, or something like that. Okay, but you understand the point is I can get rid of the quarter. Okay.
Mm-hmm.
So because I can get rid of the quarter now, I'm left with very simply my 2 tables that I asked you, how would you compute it? I asked you, how would you do it? And you correctly told me you're going to pad it with a notion of zeros, do the double flip and so on. So if you do all that, then you get that lower table answer, -1, -2, -1, 0, 0, 0, +1, +2, +1. Okay, that's what you get from it. Okay, and that table is called the Sobel table. Sobel, S-O-B-E-L, very, very commonly used in edge detection in computer vision. And definitely prior to deep learning, it was like a basic step everybody did. Okay, and Canny is another more advanced version of it, right? Which Dr. Shah did yesterday. I will not do Canny today because it's not that important for you guys to know it that much. Okay, but you do need to kind of know what Sobel is. And so notice that I told you the first approach I said that was simply derivatives only was called, I said, Roberts, right? The Roberts method, and that was 1964. A year later, 1965, Sobel came along and did the smoothening part, added the 4 ones to it, smoothened everything with that. And then for 20 years or so, people were very happy with that edge detection approach until first Marr and Hildreth came along and did something biologically motivated for edge detection. We can talk about that some other day. And then Canny came along and improved upon everybody's, and Canny's is like the state-of-the-art edge detector now, okay? But pretty much what I wanted you to see was 2 basic points here from today's lecture, okay? The point wasn't edge detection because maybe you'll never use edge detection in your projects, okay? The point was to understand that prior to what is going on in the last 10 years, convolution was something that you crafted out yourself. You were the creator of the convolution. You were the boss of whatever you wanted to achieve, and you chose your convolution to achieve whatever effect you wanted, right? So tell me, what were the effects you've seen today from convolution that we just talked about? Who can tell me what they were? So one thing in this zooming thing, I need you guys at least to cough or sneeze or blow your nose or rap your table or something, because if it's dead silence, I don't know if I lost the connection or not, right?
Hey.
Yeah, just say hey or sigh or something so that I know. Okay. So did you hear my question? I said, what did I show you today where I showed you the old-fashioned way that convolution was used to achieve some purpose that the designer wanted to design, right? The designer wanted to achieve something, and so the designer used convolution to achieve that. What were those achievements that I've talked about so far today that were that way?
Would it be the edge detection or the smoothing?
Okay, so wait a minute. You actually gave me multiple concepts there, so go slow. Okay, go very, very slow. Smoothing correctly is its own convolution, right?
Yeah.
Do you all see that? If I
Yeah.
want to smoothen an image, I just convolve it with a table of ones, right? A small table of ones, okay?
Yeah.
Just convolve with that. Now, it turns out that's not the best way to do smoothening. It's a quick and dirty way to do it fast. You don't have much time to think about it. Just smoothen it with a bunch of ones, right? Okay. The correct way is to, instead of a bunch of ones, you use a table of values that you got from a bell curve, from a bell, a Gaussian, okay? So that is called Gaussian smoothening. Okay, Gaussian smoothening is you don't use a bunch of just ones. You instead do, I can move down the slides. I do have some example of Gaussian table. I wasn't planning on going there today, but I will take you real fast to that. So I'm moving through the slides. So see, the idea here is that what Kenny observed was that Kenny said that the 4 ones by themselves is a hat or a box function, right? That means you're smoothening with a square wave. Your smoothener is a square wave. But the square wave, because it's square and has those hatty corner points, those corner kinky points, those level of kinks are preserved in the output. That means if you had those kinds of kinks in your input, those kinds of cornery behaviors, little tiny jumps in your input, little tiny kinky behavior in your input, not smooth, then this smoothener with the 4 ones preserves those level of kinks in the output. So your output is not perfectly smooth. Your output has preserved some kinkiness because the hat function or the box function, the 4-1 function, had these tiny kinks built into it, right? So instead, what you want to use as a smoother is you want to use a bell curve. So you want not this box function or hat function. You want to not use this. You want to use the Gaussian bell curve, okay? Because the Gaussian bell curve has no kinks, right? Okay. The only tricky thing about it is then you got to build out the table from the Gaussian formula. Okay, but we're not going there today. That's not what we're talking about. So the question I asked you was, I said, where was the designing use of convolution? Meaning the designer decided, I want to achieve something. So I'm going to design a very specific convolution to achieve my achieved result, right? And the correct answer, and by the way, who answered that question?
Callie.
Callie, very good, Callie. So you said smoothening as your second word, right?
Yeah.
So smoothening is one reason to design convolution, okay? You design convolution to smoothen. You want to smoothen it, and you design the convolution for it, okay? Now, the first word that you said was a little bit confusing because you said edge detection, but edge detection is the whole story, right? What other component of edge detection was there that we designed a separate convolution for?
Was it the derivative or the
Very
gradient?
good. Very good. That is the other convolution that somebody's designing in this process, okay? Somebody's saying, I want to detect a jump, and a jump is really a derivative. So I'm going to write a convolution I'm going to take a derivative and figure out how to write it as a convolution, and that's what I'm going to do, okay? So very good. So the only thing I wanted to achieve today with this presentation so far was that, first of all, that you understand now Sobel and edge detection. You understand it very deeply and thoroughly, but more importantly, from the convolution point of view, you understood that back then, people were designing their own convolutions as needed, meaning they were playing God, right? They said, well, we want it to be this way, so we'll design a convolution. Okay, and that's what convolution has done a lot of work through the 70s, 80s, 90s. People, billions of papers on it, how to do convolution for whatever, okay? So that's that. I'm now ready to change topics. And so I'm going to escape my presentation on this one. And I'm going to go to my next presentation, which is called Adder Boosting. Oh, by the way, just really quickly, I will open up my code to show you what the code looks like for the Sobel code. Just very quickly. I mean, really, I don't mean to spend much time on this. Just to show you. So you put your so you can still see my screen. Is that right, guys?
Yes.
Yeah.
Can you see the Sobel table or not? Yes or no?
We
The Sobel
only see the
code?
PowerPoint window.
Yeah.
Okay, so I did the wrong thing. I said I shared the wrong screen. Okay, so let me go back and figure out how to share what I want. So Robert, are you still here?
I'm here.
Okay, so Robert, I go to stop share first, right? Then I will restart share and then I'll reopen it up with the new thing. Is that right?
Sounds great.
Okay, let me try that. So I want the Sobel code to be shared. So I'm going to go down, I'm going to go share. Okay, now do you see some C code, guys?
We do.
Yes.
Yeah.
Very good. Okay, so here you're seeing the code for Sobel, just so that you really thoroughly know what a convolution is, right, and how it's implemented in actual code, right? So here at the very top, and by the way, can you see me move my cursor around, my mouse around? Can you see?
Yes.
Okay, so here at the very top, it says mask X and mask Y, right? And those are the tables that we just got from the Sobel convolution, numbers, right? Then we go through a bunch of stuff over here that has to do with reading in files and all that. So I'm going to skip all that because you really don't need to know any of that unless you're a C guru and you really want to know what's going on in C. Okay. The real important thing is that here you're reading in your picture. Okay. So you have the picture and you had your convolution table. And here you're actually doing your convolution code. Okay. So this double for loop up here is moving the little convolution table along one by one, left to right, top to bottom, right? It's moving it along. And this inside table here, see, MR is mask radius, and its value is set to 1 above, right? MR stands for mask radius, not for Mr. or anything like that, right? Mask radius. And so mask radius goes from -1 to +1. P goes from -1 to +1, and Q goes from -1 to +1. And that is the inside table. So the inside for loop is saying, once I have decided where to do my convolution, please go ahead and do it. The where to do it was controlled by the outer for loops, right? The two outer for loops are saying where to do it. They're moving me along where to do the convolution. The two inside for loops are saying, now that I'm there, please go ahead and do my convolution. My convolution is a 9-step, right? Because I have 3 by 3. So I have to 3 in the P direction and 3 in the Q direction, right? So I do that. And then here I'm adding up and accumulating a sum. I have to accumulate my sum because that's what a convolution is, right? I'm adding up those values, right? So I'm accumulating my sum of the appropriately multiplied picture value by the mask value, okay? And that's the sum 1 for the X direction, and the lower line is doing for the Y direction. Okay, so far, all good, guys? I just simply wanted to show you the Sobel code so that you have no illusions about how a convolution is actually done in code, right? Okay. But realistically, you guys are going to be using Python, and Python has it all built in for you, so you never have to worry about actually doing the code. But maybe once in a while, you may need to write your own code for something. Okay. So whether you use C or Python, this is how you do a convolution.
Quick question. Once you have the outpick X and the outpick Y, what do you do with those two? Because at the end, you want to end up with a single picture, right?
I'm doing that magnitude calculation right here.
Oh, okay. Okay.
By the way, it's saying my internet connection is unstable, but can you guys still see everything?
Yes.
Yeah.
Very
Yes.
good. Okay.
We
Okay,
haven't noticed on our end.
Okay. There's no, okay. And you're seeing the magnitude calculation there. I'm doing the square root of that function, right? Square root of the multiplying the squares, okay? And so that I-val is my final answer that I want to display. And that's the one that looked like my ridge image with the ridges around the chess pieces, right?
Mm-hmm.
Because the code then simply goes ahead to print that table out. See? It prints it out here. Let's just print it out. For those of you that are C gurus, you should look at these kinds of little pieces of code because there's always cutesy things you can learn about C, right? Like you have to cast the magnitude has to be double value in C because it's a decimal value. So you first have to cast it to int, then you have to cast it to char to be able to print it out as an image, okay? But anyway, so I'm done with this code, guys. If you need to know anything more about it for whatever reason later on in your projects or whatever, you can always come back to me and ask, okay? But I'm going to skip this now and go on to my next topic, which is a big one. Okay, so what can you see of my screen right now?
It's the
Code.
code still.
The code's code again. Okay, so I'm going to open up my new presentation first, and I'm going to share it. My new presentation is RU3. So Robert, did you tell them where all these files are?
They've been shared in the Slack.
Okay, guys. So I finished RU1 and RU2. That's what I showed you. So when I'm going to RU3, that file. So if you want to follow along from the notes, feel free to do it that way. I am doing RU3 now, and I'm about to share it. Okay, do you see something called AdaBoost?
Yes.
Yes.
Very good. Okay. So so now I've gone fast along, right? I've gone fast along, skipped about 20 years of work with edge detection and so on, skipping it. So now I bring you to the 2000 year, okay? So the year 2000, actually it was 1996-ish that very exciting work came out. And the work is called boosting. And the idea behind boosting is, so let me actually walk through the slides here. Okay, I'll just open it.
So the screen is frozen for me.
Can you see the add a boost or not?
Yes, I still see add a boost.
Yeah, but that's all I have because I haven't moved anything else along.
Okay, okay.
Yeah, I'm going to go now to screen. Okay, now I'm in one just slide is showing to you, right? Is that right?
Yes.
Yeah.
Okay. So that's what this method was called, add a boost for adaptive boosting. And so, of course, it does face detection like, this, right? Okay. So the idea was, let's start from the very beginning, right? So the idea was, imagine you have a rich person, and at the time, 2000, et cetera, and for a few years, I was able to talk about somebody who was a well-known rich person in the country. And so, but nowadays he's faded a little bit, but I'll still talk about him because it makes a good example, and maybe some of you might remember him. Okay, so first of all, who do you think I'm talking about?
Warren Buffett.
Getting close, getting close. Very good, very good. Okay, so the person I'm actually talking about is Mitt Romney, right? Because at the time he was running for president and all that, 2012, whatever. So I would use him as an example. I'd say, supposing a rich person, he would like to hire a team of stock experts, right? He has the records of all of them, but he can only afford a team of about 50 or so, okay? And the deal in the stock market is that every day the market's going to open up at 9:30 in New York. And what the stock market experts have to do in the morning by 8:30, so they have to call up all their clients and say, listen, we believe the stock market's going to go up today, so go and buy, right? Or it's not going to go up and then just stay put. Okay, we won't deal with the negative side because that gets a little bit complicated in this reason. Only two things go on. Either the market goes up or it doesn't go up, right? Okay, so they do all those calls. And now this rich person has the records for the last 1,000 days. 1,000 days is about 5 years because in each year there's about 240, 40 weeks times 5, right? Because, there's some holidays and this and that. So whatever. So roughly 1,000 days, 5 years of record he's got. And that means that he knows for each expert, he has this table in front of him. It says for expert 1 and expert 2 and then expert 3 and so on. And then in the grid, you've got day 1, you've got day 2, you've got day 3, you've got day 100, day 102 and so on. And the check marks and the crosses mean that at the end of the day, that expert was correct or that expert was wrong, right? Meaning whatever call they made in the morning, at the end of the day when the market closes at either 4 o'clock or 4:30, I don't remember exactly now, in New York, you check to see did the expert make the correct call or not, okay? So do you understand what this table is about?
Yeah.
Yes.
Okay, this table is not whether the market went up or not. This table is just, did the expert make the correct call or not, right? Did the expert get it right or did the expert get it wrong? Whatever happened, happened. Did the expert get it right or wrong, okay? So that's what it is. And the rich person has this information in front of him or her, to choose the experts, the team that they want, right? They can only afford 50 of these people. So the first question is, who will the first member of the team be? What's the most sensible thing to do?
Yeah, the person with the most checks.
Yeah, just pick them, right? The person with the most checks, okay? So that's what you're going to do. So, and indeed, it says at the bottom, we would pick as the first team member the expert with the most checks, okay? So that's exactly what he does. So it is a correct move to have done that. Pick the one who made the most correct perfectly. Now, how do you pick the second one, right? So by the way, these slides come from an online class of mine and actually where you were in my class. So you've seen these slides. And so it says, please spend a minute thinking about it and email your instructor with the answer. We'll pause here while we finish the task. So of course, I'm not going to pause. I'm just going to ask you guys, what do you think? How should we pick the second one? The second most best answers?
Would you want to pick the person who got the most wrong and invert their answer?
Okay, so the one who got the most wrong and the answer, and that's what you could do if your balance was that these experts were such losers, right? They were such losers, they were getting like 90% wrong and so on. But in this game, they're going to assume that every expert that you're considering is 51% plus correct, okay? So at least 51% of the time they get it correct. And if they don't, if they're getting it 47% of the time correct, then you flip the answers like you just said, right? Okay, so those ideas are kind of interesting ideas to do, to flip the wrong ones and so on. But it turns out, so what other answers do I have?
I feel like the first thought someone would have is to, for the second team member, just pick the person with the second most check marks.
Correct. And that's what
Yeah.
people were doing until this AdaBoost algorithm came along, okay? So remember, it's 1996 that the algorithm comes along, right? Until then, people are doing that, pick the first one, pick the second one, flip the extreme wrong ones and that kind of thing, okay? They were randomly doing that. It turns out the correct answer is to pick the second expert as being that who gets the most correct of the ones that the first expert got wrong.
Mm-hmm.
So you see that point? Complementing, right?
Yeah.
The second
That
expert
makes
should be
sense.
the second expert should be picked so that they complement the first. But can you believe it? It took till 1996 for this basic idea to come about, right? Okay. And so that's what you're trying to do. You're going to pick the one who will complement, okay? And then it turns out, then you're going to pick the third one as the one who complements the team so far, right? So your team has two of them so far. You're picking the number 3 expert. You're picking the third expert. So you're going to see how the first do on all your examples, and what they're getting wrong. You want to pick number 3 member as the one who gets most of those correct, right? So you understand that, how the complementing idea works?
Yes.
Mm-hmm.
Okay, so that's it, right? That's all you're going to do, and then you're going to pick your 50th team member that way. The 50th team member is going to be the one who the first 49 are still getting some examples wrong. The 50th team member had better be the one who can kill most of those examples, okay? And that's your 50th team member, okay? So that's how you get the next one. And then if you need 51 team members, then you go to 51 and so on. And generally what they found is that initially each expert is only doing around 51+% correct. A strong expert is somebody who's getting over.
He cut out for anyone but me.
Yeah,
That's what I was
yeah,
gonna
me
ask.
too.
I can't
I
hear.
can't hear him. We couldn't hear you the last like 30
Couple of
seconds.
seconds.
Okay, so let me ask you, what did you last hear me say?
Like
Hello?
how much each expert was doing?
Yeah, okay. No, my point is now I'm asking you if one of the pool of, you have a pool of experts, right? 10,000 of them or 100,000 of them or something like that. If one of the pool of experts is already getting 99.9% of the examples correct, right? Then would you even need the rest of the team?
Hmm.
You wouldn't, right? Because that
Yeah,
one
not
expert,
really.
yeah, you wouldn't need the team, right? Because the team is not going to help you get any better, right? You're already where you want to be. 99.9 is the best you can be, so you get there. This is on the training data, right? Training data means the data that you already have historically, okay? So if you're 99.9% of the training data, that's good. No point in anybody else joining the team, okay? But realistically, that's not realistic to have such good experts, right? So realistically, your experts are about 55, 65% correct, and you're getting 35% wrong, 25% wrong, and so on, right? So those experts are called weak experts, okay? They're experts, but they're not strong. Strong would be somebody who doesn't need the rest of the team. So what boosting does is that you're working with a team of weak experts, but because they're complementing each other as a team, they're able to kill 99.9% of examples, okay? And that's boosting. You boosted your performance up. You got a bump from where you were, right? Okay, and that's what boosting is. So ADA boosting, which is the name of this algorithm, ADA boost. ADA stands for adaptive boosting. Adaptive boosting, ADA boost. This, you're adaptively picking the team members based on this complementation idea. And so that's how you're able to do your boost and get close to 99% and so on, okay? So the main concept I wanted you to understand from this is that you can get good performance by having this team, right? Now let us look at how an expert actually is constructed, okay? So what is an expert? So initially, this is my attempt at art. This is my facial data. Remember, I'm given, so I was given the stock market example first, right? That was every day, day by day. And in the stock, so I'll back up to the stock market example. In the stock market example, I was given, in the stock market example, I was given day 1, day 2, day 3. And you know now, because you're the god of this process, you know whether day 1 was a up day or a not up day, right? You know that. So you could have marked day 1 is not up day, day 2 is up day, day 3 is up day, day 100 is not up day, and so on. So you could have marked them that way. So basically there's 2 classes of inputs, right? There's 2 classes of input examples. Those when the day was up and those when the day was not up, right? That's for the stock market. So for us, our game is face detection. So we want to have a training database of positive example faces and example non-faces, right? So our positive example faces are faces that you get from a facial database, which you can buy from the local Department of Motor Vehicles. All states' motor vehicles, they sell these databases of faces. You can buy them because they just faces pictures and there's no names identified to them. So they're allowed to sell them because it doesn't facial ID the person, right? So you can buy this database of faces and you could have it like this. You'd have your face 1, face 2, face 3, and so on. And then below it, you'd begin your non-face examples, right? Non-faces are like what? Trees, cars, telephones, chairs, everything else that's not a face. Even the lower part of your body is a non-face. Even if the box is covering the, the box is spanning, the upper part of the box is looking at your mouth, let's say, and then goes past your neck down to your chest, then that's a non-face, right? Also. So everything else that's not a classic face is a non-face, okay? So for us, we want to have these experts that will get some of those faces correct, some of the non-faces correct, and so on, right? And we want to have different experts. And then we want to pick from this pool of experts, we want to pick our team, right? So that's the game plan that we're going to play, okay? So is that transition from the stock market example kind of clear how I'm moving on now to faces?
Yes.
Yeah.
Okay, and my game is going to be again, pick the column that has the most correct and so on, right? Okay, so I'll pick that first, then I'll pick the next one as the one who complements and so on. Okay, that's the game I'll be playing, right? But the first thing we need to decide then is what is an expert, right? So for us, for generating an expert, we need to have firstly our database of faces. So this is our database of faces, right? This is our database of non-faces, okay?
You cut out again?
Yeah, I can't hear him either.
Me neither.
Man down.
Okay, can you hear me now?
Yes.
Yes.
Yeah.
I'm glad you guys are telling me when I need to repeat, right? Because that's the only way we can continue this communication, okay? So make sure you tell me every time I choke out. I have no idea why I'm choking out, but I'll figure it out later on, okay? I have this database of faces, and each face is 50 by 50 pixels, okay? It's a little box of 50 by 50, right? And each non-face is also 50 by 50, okay? Is that kind of clear?
Yes.
Okay, and I have many faces and many non-faces, right? Many meaning like the hundreds of thousands, okay? Then I want to create an expert. So what is an expert? So it turns out an expert is basically starts out by being chosen as one of these 4 families of patterns, okay? These families of patterns are black and white bars within a box of zeros, okay? And black and white bars means the white part of the bar is a +1 and the black part of the bar is a -1. Is each of these patterns clear? A, B, C, D? Or yeah, is it clear what these patterns are? That I'm going to have these abilities to generate these patterns, right?
Yes.
Right. So I will generate, let's say I pick the pattern A, okay? I pick the pattern A, and what you should understand is that I have many choices for that pattern A, right? Because I can move the black-white bars within the bigger white box. I can move it anywhere I want. I can make them narrower bars. I can make them broader bars. I can make them taller bars. I can make them shorter bars. Is that completely clear that I get a variety of such patterns A?
Yeah.
Yes.
Okay, so now I have to focus on only one such choice of a pattern, okay? I'm going to take one example of a pattern. I'm going to work with it, okay? So I pick one pattern, meaning I've locked in the width of my bars, the height of my bars, where I located my bars within the box. I've locked all that in, and I've chosen one such pattern, okay? Now, the total box size has to also be 50 by 50. Okay, why does it have to be 50 by 50? It has to be the same size as my images, okay? And my images are all 50 by 50, right? So now I will do the following. I will consider showing you a number line, and the number line goes from -infinity to +infinity. And I will compute a 1-location convolution between my pattern that I picked. I remember I picked only one exact pattern, right? I picked one pattern, and I've taken that pattern, and I'm going to do a 1-location convolution between it and my first face that I had in my database, okay? And can you imagine that convolution? Can somebody just maybe tell me what that convolution actually looks like then? Like, what did I just do, right? I got a face, and that could be my face, okay? I could be the first face picture in the database, right? So you know what my face looks like. It's got some light areas, some dark areas, some hair, and so on. That's my face image. Now I've picked one of these patterns, black-white bars, right? What are the black-white bars actually? What do those numbers represent in the bars? What are they?
Positive one.
Yeah, they're positive ones and they're negative ones, right? The white part of the bar is +1s. By ones, I mean the actual digit 1, right? And the negative ones are -1s, right?
Yeah.
And the rest of the pattern that is not in the black or white bar is zeros, okay? Is that kind of clear?
Yes.
So now I'm going to apply that pattern to my face, and I'm going to get what out from that? When I do the 1-location convolution between that pattern and my face, what do I get out from it? What comes out as the output?
If you're using the A pattern, correct? I think
Yeah.
it was like a
Yeah.
either a leftward or rightward edges.
Yeah. So it doesn't matter. I got a vertical bar of 1s and a vertical bar of -1s, right?
Mm-hmm.
And then I have to convolve that with my face, right?
Yes.
So what do I get out as the output, guys? Maybe I'll pause here and ask questions, okay? I'll call your name, So I'm going to ask Jenna. Ding, 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 ding. Jenna, you're the winner.
I'm not sure.
Okay, so let's try to think about what I said, okay? What did I say so far? I said I've got a table of my face, which you understand I showed you what templates of faces look like, right? They're just
Yes.
50 by 50 pixels of my face, right? Okay. Then I've selected a pattern. I selected one of my patterns to be +1s and -1s chosen in a very specific configuration out of millions of possible configurations, right? So I could have had my +1, -1s in any ordering, right? As I was showing you earlier. But I've picked one of them and I've locked it in, right? So that is my table of numbers. What is the size of that table?
50 by 50, the
Correct.
same size of the image.
Correct. So my own face is 50 by 50. It is also 50 by 50. I'm going to do a one location convolution between the two. What am I going to get out for the answer?
You would get, like, it would kind of switch.
Yeah, don't be too fussy. Don't think too much about this. The answer is very stupid, right? What is the nature of that thing that I get? Do I get a vector out? Do I get a real number out? Do I get a complex number out? What do I get out? Do I get a billion numbers out? I'm looking for a one location convolution, right? What do I get out?
I don't know. I'm sorry.
Okay, but what were the convolution steps, right?
Yeah, so like you would start with the zeros and then you would.
Yeah, and then I said it's only one location convolution, so I don't need to do the ocean of zeros.
Okay.
And I don't need to do the double flip also, right? I simply need to just take the weighted sum, right?
Yes.
So what do I
So-
get from the weighted sum?
A vector.
No, I get
No.
one number,
Okay.
right? Do you understand that I get one number? Does everybody understand that I get one number back?
Yeah.
Yes.
I need you to think through what that convolution means, right? The convolution means I took the upper leftmost number of both tables and I multiplied it and I saved it. Then I took the next number over to the right of both tables, I multiplied it and I added its multiplication answer to the first number I got. Then I added the third one over, and then I added the fourth one over, then I added the fifth one over, I added the sixth one over. Then I went down a row. I did the same thing, adding. At the end of it, I'm done with the last lower right-hand corner. I got its number, I added it into the sum, and what did I get? A big, massive, fat sum, right?
Yes.
Okay, are we all good with that? That's what I get out?
Yes.
Yeah.
Okay, now can I say, so I got one number out. Can I say anything about whether that number is going to be positive or negative?
Not directly.
Okay, let me say the following. Let me trick you for a moment. I'm going to ask you a trick question, right? So instead of the +1s and -1s in my table that I allowed myself to have, instead of that, if I just had the table.
You're breaking up again.
Yeah,
at
you
least
cut out
for me.
again.
Table of ones like the average. Hello, am I back?
Yeah.
Yeah,
Yes.
you're just not back.
Yeah, it's saying my internet connection is unstable, but I'm glad it tells me that at least, right? That it tells me that every so often. Let me see if there's something basic I need to do, okay, to make things better. No, I think I just have to just play with it, right? Okay. So you guys can still hear me now?
Yes.
Okay. So what I was saying was, supposing I restricted myself to only +1s in my table of numbers, right? I had zeros and +1s, no -1s allowed. Okay. Then, can you tell me what would the nature of my resulting answer be?
It would be a very large number. A
A very large number,
positive.
large positive number, right?
Yes.
Now, do you all of you who are paying attention and need to pay attention, you all understand why it's only possible that way to only get a positive number from that?
Yes.
Yeah.
Because I multiplied everything by +1s, right? And the original numbers that I started with in my face were all only positive numbers because an image is always positive, right? So because the image values only go from 0 to 255, right? Okay. So that's the case, I get a positive answer back. But now in my table of actual numbers, I allowed plus ones. I didn't only allow it, I required you to have plus ones and minus ones. I said you have to have a white bar and a black bar, right? So the white bar is a bunch of plus ones, the black bar is a bunch of minus ones, right? So that means that I don't know whether my final answer is going to be positive or negative. Do you see that?
Yeah.
Okay, I don't know that, right? Okay, and that's all okay because I have set my number line at the bottom on this slide here to go all the way from negative infinity to positive infinity, right? So wherever I get my answer, I will plot it on the number line as a little X. Is that clear what I've done?
Yes.
Okay, and all those of you who are trying to pay attention and to understand, are you completely keeping up so far?
Yes.
Yeah.
Okay, and let me go on to the next concept then. So then I'm going to bring in my second face, which is not me anymore, because remember, I was the first face, right? The second face might be one of you guys. The third face might be another one of you guys. And the fourth face might be another one of you guys. And that's my facial database, right? It's a bunch of REU students from the last 30 years that UCF has done the REU, whatever. Okay, I bring them all in and I start plotting them as additional X's on my plotted line here, right? Why am I getting some positive, some negative X's, the X marks? Why is some on the positive, some, why is that happening?
Because we're using +1 and -1 in our convolution.
Correct. But why am I getting that kind of variation? Why are we not all on just the positives or all on the negatives?
Because there's a different distribution. Like there's some that are more within the positive range and some more within the negative range.
Correct. And the positive and negative range that I chose with that pattern was random, right? I randomly chose a pattern, right? Out of many possible patterns, I chose one pattern. So I don't know whether that pattern is looking for, maybe if it lands on somebody's dark beard, right? Dark beard will have low values. Lighter skin might have, bigger values. So if it lands on somebody's beard, then the beardness factor will change whether I get a final positive result or a negative result, right? And the same with if it's looking at a uniform forehead area. Maybe in a uniform forehead area, here, let me ask you this question. Supposing the +1 and -1 bars, right? You all know what I mean by the bars, right? Is that completely clear what the bars were?
Yes.
Yeah.
Okay, so supposing that +1, -1 bar area landed on a uniform color of the face. So it's like the forehead where every pixel is the same value. What will my answer be? My final convolution answer?
Would it be 0?
Very good. Who are you?
Audrey.
Very good, Audrey. Excellent. Yeah. That's because, but what was required for me to be able to get that 0 as the answer? What is the mathematical requirement?
The
There's
weighted
a
sum.
lot of negative values as there are positive values.
They have to be the same sizes, right? Yeah, correct. So as long as the black and white bar are the same sizes, I will get a 0. And as long as the underlying image is the same constant value, I'll get a 0 answer, right? Very good. Okay, so you guys are beginning to think carefully about what this all means, right? Okay, about how these patterns interact with the image, right? Okay, so now we will go ahead and finish up plotting all of the as little x values. We'll plot all the faces numbers that came back, right? So we'll plot them like this. So we'll go ahead, go to the next slide. And we got a distribution like this, okay? A big hump. And you already understand what it means to get different values along the x-axis, right? I just got a different number back, right? Why am I getting those tallnesses? Why are some x's taller than the others? What does that mean in my picture? In this picture, in this figure that I'm trying to show, what does that tallness mean?
That's somewhat of like the count of how many faces evaluated to that number.
Very good. That's what it is. It's saying how often did I come back with that number, right? How often? It's the oftenness number, okay? That's all it is, okay? So it's just saying, if you start from the right, from the left over there, that extreme value was all by itself, right? One little x sitting all to the left, to the negative infinity side. Then I come and there's a tall set of 5 values. 5 values all got the same number, right? And so on, okay? So I come up with a distribution like this, right? Okay, now I can think about my distribution having an actual boundary on top, right? So I plot it, I draw it out, and then I start bringing in the non-faces, right? The non-face images, okay? So my non-faces images I'm showing as red circles. And I'm overlapping the 2 distributions. I'm overlapping them. So at the end, I get something like this. Is that process clear?
Yes.
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 Yeah.
Okay, very good. So I've done my full distribution of images, right? I convolved them with that one same pattern. Remember, I locked in that one pattern, right? Locked in the one pattern, I did this distribution, I got this plot out for me, okay? Now what I'm going to do with this plot is I'm going to look going from the leftmost possible value, and there is a leftmost possible value because there is some point. It doesn't really go all the way out to negative infinity, right? It goes up to some big negative number, right? And then the red curve goes out to some big positive number, right? So I'll go through number by number, integer by integer. I'll go through looking for what, so those are shown as the arrowheads, right? What if my arrowhead, when it's located at that position, what if it was the threshold, if it was the boundary between the 2 classes? So that means, let's say, see how I have one threshold raised higher over there, one arrow higher,
Mm-hmm.
right? So it turns out when I pick it as my threshold, I'm then going to say, I'm arbitrarily now going to say, I'm the boss of this whole process. So I'm going to say, if my number ever lands, when I give it a face image, when I give it an image and I do the convolution, if I ever land to the left of that threshold, I will call you which group? Are you the blacks or the reds?
Blacks.
Why?
Due to there being a larger amount of faces on the negative side.
A large amount of blacks, right? Yeah, the blacks are the faces, right? Correct. Okay. So is that reasoning clear to everybody?
Yes.
Yeah.
Why I would call that the blacks? Because the majority are on that side, right? So unfortunately, for those of us that have pained lives in multiculturalism and so on, and we understand that in different parts of the world, people have drawn some boundaries, and you ended up with a majority group on one side, and then another majority on the other side. But unfortunately, painfully, there are some minorities left on either side, right? On the wrong sides.
Mm-hmm.
And depending on where this process happened in the last 100 years in different parts of the world, many people got slaughtered, okay? That's just a fact, right? So, so now what we want to do is to make sure that we choose the arrowhead that minimizes that possible slaughter, right? So had we chosen an arrowhead more to the left, like if our arrowhead had been where my mouse is now, can you all see my mouse?
Yes.
If my arrowhead had been here, then I would have no minorities on the left, but I've had a huge amount of minorities on the right, right?
Yes.
Okay. So I keep searching and searching and searching and searching for an arrowhead position where I minimize the 2 minorities. Okay. And that minority constitutes my what in vision, since we're no longer talking politics and the real world.
Error?
It is the ones I'm going to get wrong, right? Because it is the red circles that are going to be said as black. We will be reporting them as black, even though we truly know they were red, right? And the black X's on the right of that margin are going to be the ones that we know are truly black and therefore faces, but we are going to report them as being non-faces, right? Are we all getting very, very clear about this process?
Yes.
Yes.
Yeah.
Okay. Now, the good news, you can ask me, well, what if the black and the red curve are drawn differently, right? Meaning I just drew black and red curves here in a certain way, right? I drew them. And I got these two distributions this way. What if my curves were drawn differently, right? You can ask me all sorts of questions like that, okay? The fact is, no matter how you draw the black and the red curve, as long as you have roughly equal numbers of blacks and reds, you're going to always be able to find such a point or multiple points that will minimize the error, right? The only time you cannot is, do you know when?
When the curves are the same?
Correct, when the curves lay on top of each other. Yeah, then I can there's no way to squeeze out a winner, right? When my curves lay on top of each other. But if my curves lay on top of each other, it means that my images are such that the classes are completely messed up. My class of faces and my class of non-faces, or whatever two classes I'm looking at, are so messed up that I get equal numbers of times a certain convolution answer when I have faces or one class, and equal numbers of times for the other class, and I have no separation. And that's a hopeless situation, okay? But generally speaking, as long as I have some separation between the two humps, I'll be able to minimize this thing, right?
Mm-hmm.
Okay, so that final threshold that I've picked for this particular expert pattern, I had the patterns of ones and minus ones, right? Specific pattern. I got it. I ran through the thing. I did these histograms. These two humps, by the way, were called histograms in case you hadn't already figured that out, right? These are just histograms, right? So I've got my histograms. I've used my threshold to find the minimum error. And then I have to give a polarity. Polarity is which side am I calling what? You know, which side am I calling the majority on one side and the majority on the other side, right? Two different names. Okay, that's polarity, okay? So, or parity, sometimes they call it. So those three quantities constitute my choosing an expert. And that's my expert, meaning the original pattern, the threshold, and the name of which side is what, right? Is my expert, okay? So now I've got my expert, and I can do that for every one of those funny patterns that you start out with, right? So you started with a pattern of ones and minus ones in a particular chosen location and all that, and I'll generate a full expert from that. I'll do another pattern, I'll generate another full expert from that. Okay, so do you understand how I get my experts?
Yes.
Okay, so then I could have spent a lot of time on going through what the actual algorithm does, because the way I told you was you will pick the second expert as being the one who complements the behavior of the first. You'll pick the third expert as the one who complements the behavior of the first two, and so on. So I could have spent a lot of time telling you how that complementation work is actually implemented in the algorithm, in the boosting algorithm. I don't think there's that much point, because it gives you very good intuition about boosting if I did all those steps, but realistically, you're not going to have to know that, I believe. So I am going to assume now that if you had to write this code up, right? If you had to write up this boosting code up, you would have had some idea how to do it. Is that generally true? Just take a minute to think about that, right? If you had to write this boosting code up, you could have written it, right? Not that I mean you would write it, and not that I mean that I definitely mean you could 100% write it, but just you have some inclination. What you have to do, you have to pick the expert pattern first, then you have to compute the histograms, then you have to go search for the minimal threshold that minimizes the error, then you report the combination of threshold, the polarity, and the pattern as the named expert, and that would be called expert 1. Then you would do another for expert 2, then you do another for expert 3, then so you build up all your experts that way. then you would go through the selection process, right? The selection process is, how do I pick from these experts who's going to be the first member of my team? Who's going to be the first member of my team? I have to pick that, right? So that will then be that I'll pick the one with the most correct and so on. Then I'll pick the second one who complements and so on. So are those steps kind of clear that that's what you would have to do?
Yeah.
Yes.
Yes.
Okay, but much more importantly, you need to be clear on just how the convolution was used and what you did with that convolution result and how you chose a threshold then and so on, right?
Mm-hmm.
Okay, because that's the stuff that's going to carry over to the next set of ideas, okay? So there is more to the boosting algorithm, and in particular, there are two parts that I'm kind of skipping. Actually, there's three parts I'm skipping. I'm skipping the actual selection algorithm because they don't do it by this complementing approach. They do it by setting up some weights. The weights go for the examples. The weights go with the examples. And every time you've gotten wrong by an expert who has been chosen so far, every time that you're still wrong, the examples weights rise. Okay, the examples weights rise, and then every time you're trying to pick a new expert, you're going through and adding up all the weights of the wrong examples, and that's the penalty for the expert. And then you're going to be selecting the expert at that moment, the one with the least penalty. Okay, so that's how they really do the complementation idea, but you could have done your own complementation without that approach, without the weights. Okay, you could have just said, I'm just going to complement. I'm just going to look for all the ones you got wrong and figure out who the next one gets correct and so on, right? You could have written that complementation rule, right? Okay, so I've skipped the true AdaBoost detail of the algorithm. I've skipped that. I'm skipping how they do, why do they pick these patterns of plus ones and minus ones? I'm skipping that. I'll just vaguely tell you what it is. You know that this is a convolution, right? That you have to do every time, right? Yeah?
Yes.
So do you completely understand that when I place in Sobel, when I place that 3x3 table somewhere, I have to do 9 multiplications, right?
Yes.
And 9 additions, right? So in this world over here, when I place that pattern of mine somewhere in an image, or let's say I place it over a face or a non-face image, how many steps do I have to do in the convolution?
50 times 50, so
Very good.
2,500.
Yes, 2,500. Hey, what was your name again?
Pedro?
Pedro. Okay, very good, Pedro. Hey, so let me ask one question. I'm seeing that Kaylee, Jenna, Audrey, and Pedro are talking to me a lot, and that's because you guys have been the ones who said you need to follow everything carefully. So are the other people still online or not? Just say a couple of yeses. I don't know.
Yeah, I'm here.
Yeah, I'm here.
So you guys are here, but you're not contributing that much, and that's fine. And I'm assuming then it's because you're kind of keeping a ear on what I'm saying, and maybe you already know some of this stuff or something. Is that true?
Yep.
Yeah.
Very good, very good. Okay, very good. So the 4 that need to pay attention are paying attention, right? Very good. Okay. So you understood that the convolution then would require 2,500 steps, right? 2,500 steps, okay? And that's 2,500 multiplications. And you'd also have to add up all those multiplication answers. So you have 2,500 additions as well. So basically 5,000 basic operations need to be done, right? For one locating over it, right? So they come up with something else. They come up with something called the integral image, which allows them to do that whole convolution thing very, very fast, okay? Within 8 lookups of a table, they can get the answer, right? Now, that has to do with pre-computing some values, pre-computing some addition areas and so on. And because they were clever enough to choose plus ones and minus ones for who the convolution weights are, right? So what were the weights in the Sobel?
The plus ones and the minus ones, or?
Yeah, they were plus ones, minus ones, and what else did you see?
Zeros.
And what else?
+2 and -2.
Correct. So there were 2s also in there. There were -2s and +2s in that also, right? So those are the weights in Sobel, okay? The weights of a convolution in a Gaussian table would be like what? Just give me a vague idea.
Bell curve.
A bell curve set of answers, right? So the numbers in the middle of the table would be very
Large.
large in the center of the table. And as you go out concentric circles away from the center, the numbers would get smaller and smaller, right?
Mm-hmm.
And so in that case, sometimes they keep the bell curve table as a table of integers, in which case some numbers are very large, or they keep it as a table of real numbers, where the biggest number in the center is set as a 1, and the rest of the numbers are decimal values going smaller than 1, right? Okay. But anyway, so you could have these different convolution tables. These guys very cleverly chose to make their convolution values only +1s and -1s, because a region of +1s, let's say, right? A region of +1s, I need to calculate the convolution between that region of +1s and the underlying picture, right?
Mm-hmm.
What is that equivalent to?
Just the sum of the values.
Very good. Very good. So because the algorithm very cleverly chose +1s as the weighting numbers, as the WEIGHTING numbers, the result of the convolution is simply the original sum of the pixels, right? So they go ahead and they pre-compute some table of summations of pixel values, and then they look those up in a very clever way so that they can get the region of convolution, that region of +1 convolution, they can get it with only 8 table lookups.
Mm-hmm.
Okay. They can similarly get the negative ones, right? The -1s. Similarly get those, then they add them up together and they get the final convolution answer, okay? So within about 20, 25 lookups in a table, they've done the convolution that otherwise would have been 2,500 calculations, right? So they do that very fast. Then there's another thing they do very fast, has to do with the number of experts that they pick. And I'll just sketch that idea out for you. It's not important at all. You'll never use it at all in anything that you're doing this summer, but it's a good idea to know about and think about. It is that they found that if they were trying to get 99% correct on the testing and training, 50 is not really the right number of experts. You need like 300, 400 experts, okay? So they found that, right? So then they said, so now you're given a bigger image as input. Bigger image as input. It's a group photograph. Maybe the REU's group photograph. You might have seen it on our website in the past. The REU pictures. This year we'll have a hard time taking that kind of picture because you guys are not all in one place, right? So we'll have to be satisfied with taking these Zoom pictures, right? Differently seated people and so on. But anyway, imagine a regular group photograph where, you know, social distancing was not happening, or even not a group photograph. Imagine it's an image of a store and it's trying to find the faces in the store, right? So when you cut your 50 by 50 region out from the input image now, so you're given a test input image and you're supposed to now tell us whether there's a face in there or not. So you're supposed to go and cut out a 50 by 50 region at the upper top left and you feed it to the algorithm, right? You feed it to the algorithm will come back and say, you know, either the team says you're a face or the team says you're not a face, right? So most of the time, what are you going to be saying in a normal image?
What do you mean?
Consider a normal regular image, a normal regular randomly chosen image from anybody's photographic camera, right? A normal thing.
Oh, I see. So someone smiling?
No, whether someone's smiling or not, anything, any photograph taken of anywhere, take all the photographs in the world today, okay? Whatever they are, right? And your job is to go and find all the faces in them. That's your job, okay? My question is, when you consider any random image, and you start out looking at the upper top left, cutting out a 50 by 50 box first. Then you're going to move over the box to the next 50 by 50. Then you're going to move over the box to the next 50 by 50. You're going to keep doing this, right? Scanning along, looking for where there's a face, right? Where will the algorithm say, yeah, that's a face, right? How many times will it say, yes, there's a face?
Out of all the images in the world, very
Out of all the
very
images in the
few.
world, and for every one of those images, you're cutting the boxes out, right?
Yeah, so not very many times.
Very rarely, right?
Yes.
Very rarely will you say there's a face. So when your problem is that way, that what you're looking for is very rare. When your problem is that way. Now, when I teach this class, I talk about two equivalencies in real life of the same idea, okay? One equivalence is the political primaries, okay? And since we're in a presidential year, we had a primary recently, and I can talk about the one from 4 years ago, and then another one 8 years ago, and so on, presidential primaries. So the question is, only one of those people is actually going to be the president, right? Only one of those people, okay? So you have a lot of losers who are going to be applying and going to be in contention. They're going to be competing. Just like in this face detection task, you have a lot of competing boxes that are all trying to be a face, right? But yet the true winners of faces are going to be very rare, right? Very few boxes will be classified as a face, right? Very few of those presidential contenders are going to be the president. Very few, different topic now, very few of the first grade class across the nation any year, very few of those people are going to end up with a PhD, right? So in the presidential situation, or in the figuring out which of those first grade kids is going to be a PhD situation, does it make sense to run the complete test of life, the complete test with all the voters, all the experts voting? Okay, so the presidential primaries, it would be instead of each state running its own primary, you'd have all the voters voting on the presidents, on all the candidates, and then you would drop out the lowest three, right? Or the lowest two, you drop them out, and then you'd vote again next week. The whole country would vote again next week, and you do it all over again, then you drop out the next three again, the bottom three, and then the following month, you'd have another primary, and the whole country would vote again. Okay, do you see the different way that I'm talking about it? Like instead of what they're actually doing, what do they actually do instead for the primaries?
They only have a small number of people voting.
Correct. And that's the same way as when you're trying to figure out who are going to be future PhDs amongst that first grade of class, first grade of 6-year-old kids. You only have a few experts asking the question. The experts in that case is the teacher in that classroom, right? You only have a few teachers saying, yeah, this kid is smart, this kid is not smart. You don't want all the teachers in the US to decide that, right? That would be too expensive, right? At the first grade level. So you basically do it by having smaller teams of experts. So in the voting case, it's a few experts. First, it's going to be, Iowa, right? That does it. Then who's the second one, by the way? I'm testing to see how much you guys really know about politics. Who's the second team of who?
New Hampshire.
New Hampshire's the second one, and then it goes to, I think, what is it, South Carolina or something? Yeah. So the thing is, those are separate specialized teams of experts, right? Instead of all the experts all at once. So what these guys did in the face detection thing for finding faces in the pictures, they set up a series of cascades identical to the political primaries, right? They have one small team of experts look at all the images coming in, and that team is not making the final decision. It's just making the first partial decision, right? It is culling, it is killing the definite losers, okay? It's a little bit like what happens in grade school as well. You know, some kids are so unsuited to life in an academic world that they will actually fail the first grade. Did you know that that really happens?
Mm-hmm.
And then they go on to second grade. The whole passing group goes on to second grade. And out of them, there's some kids that will fail the second grade, right? Very few, but they fail it. Then there's third grade, fourth grade, fifth grade, seventh grade, 10th grade. More people are going to fail and not go on, right? 12th grade, they finish 12th grade and they decide they don't want to go to college. So in that sense, academic sense, it's a failure, right? They don't move on, right? And then they go to freshman university and again, dropouts, second year university, you know, sophomore year, dropouts. Finally, they finish that, then bachelor's degree, then some people go on to get a master's, maybe drop out. Some people eventually go all the way to the PhD, right? Okay. So you can think of each one of those as being a set of stages, just like the political primaries, a set of stages, but looking at fewer and fewer of the set to be decided amongst, right? So fewer presidential candidates make it to the very end. Fewer people make it to the PhD pathway at the very end because they've gone through these stages. And it turns out breaking the task up into stages is the most efficient way to do it, rather than trying to do it all at once. So here's what they're really saying in the face detection thing. They're saying in that upper left corner of the image, which you know there's not going to be a face there, because the upper left corner of most images is some boundary of the picture somewhere, right? Random boundary. So most of them, there's no face there. So they're saying, why spend all 300 experts of yours? 300 experts can do the job very well. 300 experts can tell you definitely whether that's a face or not. Why spend all 300 looking there when most likely that subset of pixels, 50 by 50 pixels, is such a loser, it can be detected by maybe 20 experts only. 20 experts with a very, very strict threshold for failure. That means, so that's a little bit like, you know, in the, let me go back in my slides here, okay? In this plot that I have here, right, the black and the reds, can you still see it?
Yes.
Imagine I moved my threshold not where the central thing is, that arrow at the top, but it's more far to the left. And that way, what have I done if I move my threshold far to the left? What have I actually achieved by doing that?
You've decreased the error rate for the non-faces, or for
the reds, right? The reds,
yes.
right? I got no red failures, right? No red failures, okay? So while I've allowed a lot of blacks to go through, a lot of black examples to go through as though they're reds, I call them reds. So imagine the reds is the passing one. Reds passes, and blacks is the ones that are failing. So I move my threshold way to the left. So I have no failure reds. But I have lots of wrong blacks that I let through, seeing their faces, right? So it's kind of a little bit what goes on in the political primaries. A lot of losers still go on past Iowa and past New Hampshire, right? There's still losers going on. But the theory is, don't worry about it. Somebody else will take care of them later on, right? That's what the stages idea is, right? The cascading stages idea. The same thing for the PhD. Don't worry about, don't identify this little kid as so ultra gifted Johnny in first grade. It's okay, he's gifted, that's fine. But let him go along, you know, let her go along, let Katie go along. And 10 years later, 15 years later, we'll see if they get a PhD or not, right? Because somebody else will take care of that step later on. So it turns out that in faces, in this detection problem, that by doing it that way, you are spending lots of time on the true faces. But the true faces have to make it all the way through the stages, right? Just like a presidential winner has to make it through all the primary steps. A PhD has to make it through all academic steps, right? So in this case, a face, which is going to be a true winner, has to make it through all the smaller teams of experts, has to make it through all of them. But the non-faces, the losers, some of them are making it out early, right? With only one team looking at them and they're out. Another set is looking with maybe two teams that look at them, they're out. Another set, three teams look at them, they're out. So you did your rejections much faster with many few experts. You see how the speed up comes from that?
Yes.
Okay, but that idea is only useful when you know that what you're looking for is very rare, right? You can set it up as stages, okay? So these guys, the authors of this book in 2000, they set up two very fast making things for the algorithm to be so impressive back then. One was the business of the stages algorithm, and the other was the business of the pre-computing the summations of regions, right? So that the telling me what the convolution result was is a simple lookup of 8 values in a lookup table, okay? So because of that double speed up that they had, they were able to show for the first time at a conference in Vancouver, British Columbia in Canada, they just literally turned on their laptop and was looking at the whole audience. The webcam was looking at the audience, and as soon as they turned it on, it had drawn all the boxes for all the faces in the audience, right? And people were like, wow, we have never seen anything like this, right? But anyway, so it was a very impressive piece of work because of those extra speed ups and all that. But the only thing we care about for us here is the basic ADA boosting and how the convolution played into it, okay? Because what I want you now to think about, okay, so think about what's really going on with the convolutions, right? I've got a test box, okay? Somebody came in with a 50 by 50 test box and tells me, please tell me whether this is a face or not. Okay, so what am I doing? Well, one part I did not tell you about the algorithm is that after I've picked my team of 50 or 300 or whatever, after I've picked my team, I have to have them work as a team, right? Work as a team. Okay, I did not tell you that step. Okay, so that is an important step. So let me just quickly tell you that. So each team member that has made it to the team, right? My special team, right? Each team member will call it either a face or not a face, right? They'll make a call, okay? When they were selected for the team, they also get their own fatness weights. That has nothing to do with the weights of the examples that I talked about earlier. Nothing to do with that. This has to do with the weights on how good they should be trusted as an expert, okay? So each of them gets that number. And so at the end of it, the final decision is made by simply a tug of war between the two teams, right? You add up all the weights of those saying, yes, I think it's a face. You add up all the weights of those saying, no, I believe it's not a face. The heavier team wins, okay? That's how the final decision is made, right? So now I ask you, somebody gives me a box, 50 by 50, and I have to use this algorithm, this AdaBoost algorithm, to say if it's a face or not. Doesn't mean I'll be correct, but I have to come up with an answer, right? What are all the steps in getting that answer? I already have my teams made up. I know who my teams of experts are, so I don't have to recompute my teams and all that. That's already done for me. I've done all my training for the algorithm, right? So I just was given a new test picture, and I was given a 50 by 50 box from it. And I have to say, is this box a face or not a face? How do I do it?
So you go asking each expert individually, and then you take the weighted sum?
Very good. So firstly, when I ask each expert individually, what do I have to do for that work?
One location convolution?
Between each expert pattern and my picture, right?
Yes.
Okay, now, those of you that are not talking, are you following this reasoning?
Yes.
Yeah.
Okay, so I have to do the one location convolution, right? When I do that, I get what back?
An integer?
An integer back. Very good. What do I do with that integer?
Plot it and then compare it to the threshold.
Correct. I just have to compare it to the threshold, right? It's either above the threshold. And then that threshold told me the polarity, which side of the world was what. And that's how I make my call, right? I say either I'm a face or not a face, right? Okay. So that's how I do each expert. Then I put these experts together and the heavier team wins, right? And that's my final decision. Okay. Very good. So what is very, very, very important here is to understand what was each of those convolution patterns doing for me for this algorithm, right? Now the authors claimed, and I'll share with you, I'm going to stop sharing this thing and I'm going to open up the original paper just to show you a couple of things, okay? So you should have seen my screen disappear or something. Is that what happened?
Yes.
Yep.
Okay, now I'm going to go open up what I want. Let me make sure I can do that. Okay, by the way, Robert, what is the plan for lunch and so on? Lunch break, I mean?
In the schedule, it says 1 p.m. to 2 p.m.
Okay, so I have 1 more hour, right? That's good. Okay. That's
Yes.
good. Very good. Very good. Okay, and then did you guys need to take like a short 5-minute bathroom break or something right now? I've gone for 2 hours already. Do you need a bathroom break?
I think we should take a little break, Dr. Lobo.
Okay, let's take like a 5-minute break and come back in 5 minutes. Okay, and then Robert, if you can make sure that everybody's back when they're back, I'll ask you that question, right? So you try to
No
come back.
problem.
Okay, thank you. Okay, so in
Okay.
5 minutes we're back. Okay, guys, thanks. Bye.
All right. Yes.
Okay, so that is the research paper that we were just presenting from the AdaBoost algorithm, right? The paper was 2001, as I said. Now I'm going to go ahead and show you what they claim, okay? I believe nobody was able to reproduce this particular part of the story. So these were the choices of families of 4, right? You understand there's 4 kinds of different patterns, okay, that they had, right? Okay, so you see the 4 patterns there?
Yeah.
Then this was how they did that whole business of efficient calculating of the summations of the convolution. Okay, but I'm not going to tell you the details of that because it's not that important for us, right? Okay, this was all that. Then they went on to the business about the stages thing. I talked about the political primaries and all that. That is all here. The political primary, you're going through stages and you're kicking failures out, but otherwise you go on all the way till the very end, okay? Okay, now what they claim was that if they look at the first 2 experts that were picked by them, by their work of running the experiments, they said these were them. See, do you see that?
Mm-hmm.
They have the horizontal black and white bar, which they believe are related to looking at the patterns of people's eye structure, right? The darkness above the eyes and the lightness below the eyes, okay? That's one. That's one. And then the second expert they believe was the black, white, black one, right? Right, because that was another pattern in the families of patterns they could have had, okay? So they said that was the second expert, and that truly is true of 99% of the population. Their eyes will look like that, right? Eyes will have a central, brighter area in the middle, no matter what color your skin is. And then the darkness in the center of the eyes, typically, right? Very few people have it reversed, okay? Where their eyes are brighter than the nose bridge, right? Okay, so they claim that this is what the meaning of these experts are, right? That these experts are being selected along which ones are good for telling faces, right? Okay, so you guys are getting some idea of what might be going on with these experts?
Yes.
Okay.
Yeah.
So obviously then if you have people with beards and so on, then some part of the expert pattern is going to look for beardnesses and it's going to contribute, and you know, and you're looking for something else and this and that, whatever, eyeglasses, etc. Okay, so the point is, when I give the algorithm a test image, a 50 by 50 test image, I give the algorithm that. The algorithm runs through my set of chosen selected experts, runs them one by one through it, and they come up with a prediction, with an answer, and then you have to put all those answers together and choose the fatter team, right? Okay. So the point is, what is the role of those individual convolution patterns, right? What is the role? What is the purpose of the individual convolution patterns? Well, each individual convolution pattern was selected because it does well at telling the differences between faces and non-faces, right? That's why it was selected, right? It does well, but it doesn't do well on its own, meaning it's not how well it does. How was it actually selected? What is the rule for selecting it?
It complements other.
Yeah, it does well compared to the others who are failing to do well in those certain examples, right? Certain examples are very tough, okay? Now, by the way, what are tough examples, right? So in face detection, tough examples are, there's some humans, some real humans that have very, very rough faces. I always used to say Mick Jagger had a very, very tough face for a face detector to find, because it always seemed like, he'd done too many sun and drugs over the life that his face is kind of cracked up and taken on a different kind of shape and so on. But then I looked at another picture of him recently, and him as a younger person, and it looked like he always had a slightly distorted face. But anyway, so I don't use him as an example anymore. But there are people whose faces are just very, very craggy and not quite fitting the normal pattern and so on. So that'll be a tough face example, okay? Meaning most experts will get that face wrong, right? And then you have non-faces that come from like rocks and man on the moon images and all that. I don't know if you guys have seen any of those things. Sometimes you see a picture of a window pane of glass, and the light is just shining on it the right way, and it kind of looks face-like, right? So a face detection algorithm is sometimes going to get those as faces. And I have an image which I'll pull up later on for you guys. I don't have it ready to show now, which is a classmate pictures at a graduating class, taking a picture against a brick Princeton-like building. Like, how Princeton has those old buildings with old rock in them, old block rock. So it's that kind of building. And one of those rocky patterns, it turns out, it looks like there's a face embedded in there, just naturally shape of the rock, right? So that would be the kind of one where an algorithm will have a hard time saying it's not a face, right? Okay. So those are the difficult examples for the algorithm, meaning the algorithm will find some faces very hard to say they're faces, and some non-faces very hard to say that they are not faces, okay? So in those cases, you may have some experts at the very end come in and kill those examples. Killing it means getting it correct, right? So they were not popular, they were not strong experts at first. They were not able to get large contributions at first, but later on they're contributing to getting the difficult examples. So that's how they get selected on the team, right? Okay, so either way, the point is that you're getting this complementing convolution approach to finally winning, right? You win because you've chosen the right complementary convolutions from out of what? How did you pick your convolutions? What was your pool of selections that you could have had? Did you guys hear my question?
Yeah, I heard the question. I'm just not sure.
You know the question means? What I'm asking you to think about?
Not exactly.
Okay, so what I said was you chose those 50 team members, right? You chose them, right? You chose those experts, right?
Mm-hmm.
Who was your initial pool of experts to choose from? Meaning, who have you not chosen? Just tell me a story about the who that you have not chosen.
The ones who did not perform well.
Okay, but what kind of patterns were they?
You mean like the blocks of white and black?
Yes.
Maybe the ones who were not good at detecting any kind of facial feature.
Very good. So if you think about our face detection task, the face is typically centered in the mugshot image, right?
Yes.
So the upper corner of the image, the upper right corner, the upper right, upper left corner, lower right, lower left corner of the images are probably not contributing to detecting faces, right?
Yes.
Yeah.
So most likely anybody whose black and white bars were in those regions will have little chance of being selected, right?
Mhm.
Okay. Then out of those in the center of the face, those that are not exactly lining up where noses line up and where cheeks line up and where lips line up and all that, those that don't line up exactly there are also not going to be selected, right? Or if they're too close to others that are being selected, they might be similar, you know, because you're allowed to, in your pool, initial pool that you're going to select from, you're allowed to vary even just by 1 pixel over. You know, you move the +1 bars over by 1 pixel over, and that's a new expert pattern, right? You move it by 2 pixels over, it's another new expert pattern, right? So maybe there are equivalence classes. There's groups of them that would have performed similarly, but now you already chose one from that group. So the others don't have a chance of being chosen anymore because they're not going to complement, right? Do you see
Yeah.
that point? Do you see that point? Okay. So those are the kinds of patterns that are being rejected. Okay. Either they're redundant, they're doing things that the team is already doing. They are way far off. They can never tell a face from a non-face because they're not looking at the right information, right? They're looking at the wrong corners of the image, right? So you're choosing the weights based on a menu of weights to choose from. By weights, I mean the patterns, right? Because those patterns are just weighted sums, right?
Yes.
Yeah, yeah. Okay, so those patterns are just weighted sums. So you're choosing, you have this huge menu to choose from. It's like a buffet, infinite buffet, right? You have an infinite buffet of patterns to choose from, and you're simply choosing the ones that give us the best results. Best being defined as those that complement, right? Okay, and those are the winners, okay? So now I'm going to take you directly now to neural networks, okay? Because it makes the most sense. There is a third approach that if I have time later on today or some other day, I'll just talk about a little bit, and that is called support vector machines, okay? It turns out it also will do something very similar to both AdaBoost and neural networks, but yet different enough that it doesn't seem to have currently the same winning flexibility. But I say currently because there's something that I observed very, very interestingly about faces. So this face detection task was a challenge for like 15 years or so, okay? Started off in about 1980, 85-ish, 1990-ish, started out, and basically got wrapped up in about 2005, right? Along the way, what I found was that these 3 or 4 different competing approaches, right? Different competing approaches were all like, you know, would overtake each other every couple of years, right? So one approach would be winning 1 year, 2 years later, another one of those 4 approaches would come up and win. Again, a couple of years later, you know, one of the ones you thought was definitely a loser, was never going to win as an approach, would suddenly show that they could do well on the face detection task because these faces were out there. They were test cases, large databases of faces to test your algorithm on. So I noticed this jockeying for position that went on. They would jockey and push each other out of the way and then finally win and so on. So I don't know that any one of these approaches to machine learning is a complete failure, right? I don't know that. All I know is that I saw them overtake each other when things were not deep neural networks, right? When things were not deep neural networks, they were overtaking each other and there was no clear winner at any time. Then deep neural networks came along, and you'll see what that is. By the end of today, you'll know what a deep network is. They came along, and now deep networks allow you to do so much more than just face detection, that people are doing this so much more game, right? But I don't know that those other approaches cannot be adapted in that deep way to also make them strong. So all I'm telling you is don't put any method to death. Don't say it's a useless method, it won't do anything, because we don't know. Some team might suddenly show that it does as well as deep networks someday, okay? But basically, I'm ready now to pivot to deep neural networks. But before that, I have to talk about simple neural networks first, And so I'm going to spend the next just under an hour doing that. And then we'll take a lunch break. Then we'll come back after lunch and do some more. Okay. So I'm going to stop sharing my screen now, guys. Okay, stop sharing. I'm going to now pull up the deep neural network slides that I have, which are so by the way, maybe I'll just ask a meta level question, like a question about the whole process. Are those of you that are new and all that, have you kind of understood more or less what I've done this morning? I'm not asking you to remember what I did because I told you too many things, right? There's no way for you to remember all the things, but of course the slides are there. You can look at them later on. But did you understand what I'm doing? Just the way that I'm doing it and the way that I'm talking and what issues I'm what questions I'm asking you to get you to think more about things and so on. Is that style working for you?
Yeah.
Yeah.
For me, it's great.
But I mean, you're following and you're keeping up. You're with me, right? You're okay. That's good. Okay, that's
Yeah.
what I wanted to hear.
For sure.
Okay, so now I'm ready to go to neural networks 1. Okay, so I've got the slides up for me. I just have to pull it up for you now, guys. So let me go ahead and do my screen sharing thing again. Zoom first. Okay, so screen share my screen. And I want this one. Okay, so do you see a slide that says Introduction to Neural Networks for CAP 4453?
Yes.
Yes.
Okay, and on the PowerPoints, that's my RU number 8. Okay, so I skipped some on the support vector machines to get here. So we are in RU 8. Okay, that's the slide I'm looking at. Okay, so now I'm going to move along and let's see. I hope this works for me. I'm having some issue. Okay, so a single neuron, right? The basic idea. We'll have, and you're probably going to see this. If you haven't already seen it, you'll see it in somebody else's lecture as well, because you know, different people will bring up neurons to you at some point to talk about it. Okay, so the basic idea is you have a single neuron that looks like this. Some inputs. The inputs here are 2 and 5, the values, and I'm trying to move along. I think I have to. Okay, yeah, I'll just use my fingers to swish my screen. Okay, and then those values are going into the circular structure, but along the way they're going with some weights, right? So the weights are 0.5 for the value x1, and the weights are minus 0.3 for the value 5. Okay, so they're going in, and then they're simply going to be added in there. So these are, and then you also have the lowest one is it's called a bias term at the bottom. I'll tell you about that later on. So they're all going to go in and they're going to be added up. You see how it says computation step 1, weighted summation to perform linear modeling. Okay, don't worry about linear modeling and all that, but it's a weighted sum. So you see we are getting a value z out. Z is our result. We are multiplying W1 with X1, multiplying W2 with X2, and we're adding in the B, which is called a bias term. Okay, so we add up all those 3 quantities, 3 products, we add them up, we get an answer Z out, right? And within the circular structure, I'm showing you how the actual detailed numbers worked out for that particular example. So we have five values, 3 on the beginning of the arrows, 2 is weights on 2 of the arrows, and then I do all that addition and I get this number minus 0.4, right? Okay, so that's where I am at this point of the calculation. Now, that's called linear because I simply did a what is called a one location convolution or a dot product between 2 vectors. You can think about the x and the b's as being one vector and the w's being another vector, okay, of values. And I'm taking a dot product or a scalar product between them. I'm just multiplying them. So what linear means is that if I change my x's, let's say I double my x values, each of my x values, I double them, then I expect a doubling of my final z value. Okay, that's called linear, right? So it would be nonlinear if I was to take my x values and square them or something like that and then add them up, right? That would be nonlinear because at that part of the game, if I doubled my input values of x's, I would no longer just get double the answer. I'd get the square of the double, right? So it would be a different answer than the doubling. Okay, do you see the difference between linear and nonlinear?
Mm-hmm.
Okay, so linear is simply, you're just multiplying things out and no squarings or sinusoids or logarithms or exponentials or anything, nothing like that's going on, just very simple, multiplications and addings, right? Okay. Now, what they found in neural networks is that in order to model complicated behavior, to have complicated learning, you need to have some non-linearity thrown in, okay? And you're going to find out that that's really the power of these neural networks, is the fact that they can stack up many layers of non-linearity, they can stack it up and therefore model very complicated behavior, okay? But we'll get there slowly. So for now, what we're doing is we're simply adding in a small amount of nonlinearity with something called the sigma function. So the sigma is defined as, the sigma function is defined as, it's going to take your z value that you got from the z equals w1 times x1 and so on. It's going to take that number. It's going to feed it into the sigma function, and that sigma function will put the z here in the negative exponent, and then it's going to calculate and come back with an answer, right? So that is clearly nonlinear, okay? And indeed, this sigma function is called a sigma function because it looks like a sigmoid shape. Sigmoid shape is here. I'll just skip for a moment. I'm skipping to something called the activation function slide, and you're seeing the sigmoid shape. So see, the sigmoid shape looks like it's like reverse integral almost, right? Or it's like it's like a longer version of the integral sign, right? So that's the sigmoid shape, and that function that we just had with the 1 divided by 1 plus e to the minus z plots that way as the sigmoid function, okay? And its purpose, it turns out, is to focus a lot closer to 0 and have kind of almost linear behavior near 0, and then away from 0 as you get close to where the curve begins to turn and become parallel to the x-axis. Once you get out of that window, you're kind of flattening the result out. So no matter if your input z value was very large or very negative, very large positive or very negative, large negative, it's going to give you either a 0 or a +1, flatten it out, and only give you the linear behavior close to the 0 part, and then just have that turning going on at the two ends of the linear part, okay? So all of that together constitutes the nonlinearity that it brings into the story. And that's a big deal, okay? Because, now I'm going to go back a slide. So what you're basically doing is you're taking the z value that you got, right? And the z value that you got, if you look at where it says computation step 1, look at where my mouse is right now. It says z equals w transpose times x, okay? So this transpose, I don't know how many of you have seen linear matrix algebra. Maybe I should ask that question because that will come up in other people's presentations as well. So you need to identify yourself as somebody who's never seen any linear matrix algebra, if that is true, right? So people can slow down for you, or maybe just you can go and actually study up a little bit on it as well, so that you know what this basic notation that people will be using is. So let me ask you, who has never seen a linear matrix class?
I haven't.
I
Okay,
haven't
your name-
either.
And your name is what again? Name, sir?
And Jenna?
Okay, so Jenna, and who was the other person? And Audrey?
Yes.
And Joe.
And who?
Joe.
Joe also has not seen matrix algebra, okay? So,
I have not seen a linear matrix class, but I've learned a bit of like
Okay.
matrix and linear.
okay, and your name was what?
Pedro.
Okay, Pedro. Okay, fine. So that's okay. But you know, you did see simple vectors in high school, right? Is that right?
Yes.
And I take it you've seen vectors in not calculus, but in physics classes as well. Is that true?
Yes.
Yes.
the ijk vector and all that, right? Okay. So vectors are lists of numbers, right? And then matrix algebra teaches you things that you can do with it, right? So of course, all of this originates from trying to solve the basic problem of linear equations that you would have studied in middle school or late middle school or early high school, which is that, 5 apples plus 6 bananas cost me $10. And then I have 13 apples plus 25 bananas cost me $30. What is the price of an apple and a banana, right? You all remember problems like that?
Yes.
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 Okay, so that's called a simple linear problem, okay? Now, that problem in middle school and early high school, you solve it by doing substitution and elimination and so on. You first eliminate a variable, then you substitute and so on. You do it that way, you do it in multiple steps. A matrix approach to it firstly takes that problem and sets it up as a matrix, okay? When you set it up as a matrix, you haven't actually done any real calculation. You've only changed the notation. So maybe I should now open up a whiteboard. Robert, do I have a way to do that? Robert? Hey, Robert, are you there? Hey, are the rest of you guys there?
Yes.
I
Yeah.
am.
Okay, so maybe Robert just took a break or something. Okay, and that's fine. Let me think. Do I need to go through
Not
some?
sure. I'm not sure if Zoom has a built-in whiteboard, but perhaps you could just screen share like a OneNote or something like that and just draw on OneNote and screen share it.
The thing is, I haven't used a lot of those OneNote things. Yeah, I've used the Zoom.
Use
Zoom
MS
I think
Paint.
it has a whiteboard. If you click share screen, I think there's an option that comes up whiteboard.
Yeah, let me try that. Okay, let me just try that real quickly, okay? Just to do some basic matrix algebra stuff so that we're not completely...
Dr. Lobo, did you need me? I stepped aside for a second.
No, that's fine. Just how to use the whiteboard. But I think I got it now. I'm going to use the whiteboard for a moment, okay? So guys, do you see a whiteboard in front of you?
Yes.
Yes.
So I'm using my little pen now on it. So imagine I said 5 apples plus 3 bananas equals 10. And then I said 7 apples plus 7 bananas equals 20, right? If I do that, then of course you saw problems like that in school, right? And you would do it by first elimination and then substitution and so on. Now, the other way to do it is to just totally different way to write this down is to say that you're going to develop a matrix of 5 and 3 and 7. Now maybe I'll change this to 8 over here. Okay, just keep it different, right? 7 and 8. So that's my one matrix. And then I have a vector times A and B. And that is equal to another vector called 10 and 20. Okay. So all I did was I did not do anything terribly smart here. I've just done a change of notation. I haven't even solved anything. I haven't even done any algorithm steps. I've done nothing. I've just converted from one language of expressing the problem into another language of expressing the problem. It's like going from English to Spanish. That's all I've done, okay? But you need to know how to do that translation, right? So the above translation above is the one that you already saw in middle school and everybody understands what it is and everybody knows how to solve those problems, right? The one below, I set it up as something called a matrix and a vector and so on. So the way that you convert between one notation and the other is you are taking this pair and you are toppling it over. You're doing a one location convolution with that pair there, right? See, do you see how in the equations above, that's basically what we're doing? We're taking the 5 and the 3 and we have one location convoluting it with A and B. Do you see that?
Yes.
And then we got the value 10, right, from that? Because that's what the equation said above, right? So I go across, I take this tower over here, this tower here, and I topple it one at a time over each of these rows. First with this row, I do this first, and I get that answer. And then I do it with this row, and I get this answer here. Is that part of the notation thing clear? How I got from one notation to the other?
Yes.
Yeah.
So I have the notation above that you all understand. I was given two equations. Now I go to the notation below, right? And the notation below is the matrix notation, where I have said I have a matrix here. Sometimes they call it the matrix M, right? That's the name they'll give it, M. And they have a vector AB, the vector AB here, right? So I'm multiplying the matrix M by the vector AB. And the multiplication is done by what I just told you, the toppling and the one location convolutions. And then I line it up with this number here. And then I do the other one, I line it up with this number here. And that's how I get these equations here, right? Okay. So do you all feel that if I just asked you, if I gave you a bunch of equations, like in the upper system, and asked you to convert it to the lower system, do you all feel you could do that now? I'm not asking you to do it, but if I did?
Yes.
Yeah.
So you all understand that basic stuff, right? Okay, that's very good. Then the other thing about matrices is that, so let me now clear my screen. The other thing about matrices, clear all drawings, yeah, clear all my drawings, okay? So the other thing about matrices then is that I can have a matrix with A, B, C, and D. This is A. And then I multiply it by another matrix with E, F, G, H, I, J. And I can perform this multiplication. So there's implied multiplication over here. It's implied, right? That there's a multiplication going on there. That multiplication is implied. I can perform it because the number of this guys over here that I have to topple over these, they pair up, right? Their numbers are the same. So it's a two values in each one. So I can do this mating. There's no genetic abnormality, right? There's no mismatch. It's just, I don't have 23 chromosomes and 22 in the other or anything. I have exactly the right numbers, right? So I can do this marriage, okay? So the size of this one is 2 by 2, right? This is a 2 by 2 table I just showed you here, right? This one, 2 by 2 table. This is a 2 by 3 columns. So it's a 2 by 3, right? So in order to make matrix multiplication work, these two inside numbers always must match up, okay? Right? And the resulting answer will always be the outside number size. Right? Because I will do the E and the H with the A and the B and I'll get one number. Then I'll do the F and the I with the A and the B, I'll get a second number. Then I'll do the G and the J with the A and the B and I'll get a third number. So that's how I'll get my 3 at the end over here. You guys clear on that?
Yes.
Yeah.
Okay. So these are just simple matrix notation things I wanted to do to make sure that we're not completely lost. Okay. Now, what we sometimes want to do is we want to take a vector with 1, 2, 3 values in it, another vector with 1, 2, 3 values in it, and we want to multiply them out. But that is not matrix multiplication. Why can I not do this as a matrix multiplication now? Can you tell me that? Well, actually, wait a minute. I could. I could. But if I did these as a matrix multiplication, wait, I have a 3 by 1. No, I could not do it as a matrix multiplication. 3 by 1, and I have a 3 by 1. So I cannot do it, right? Why can I not do it?
Because the height of the second one is not equal to the width of the first one.
Yeah, because the inside numbers don't match, right?
Correct.
Okay. So I'm not allowed to do matrix multiplication on these, but I'm allowed to do what is called scalar multiplication. And scalar multiplication is basically a one location convolution between these two lists, right? So I'm just simply going to take these two numbers, multiply them, and take these two numbers, multiply them, these two numbers, multiply them, and then I'm going to add them up. And that's what a dot product, it's called the dot product of two vectors. It's called the scalar product of two vectors. It's called a one location convolution. These are all the same things between two vectors. But when they write this down, right, when they write this down in notation, they say the vector W times the vector X, and they put a transpose on this, because transpose means that I took this vector X and I laid it down on its side, right? So my structures look like this now. I laid it down its side and it looked like this, and the other one looked like 1, 2, 3. And now I can multiply those two things out in normal matrix multiplication. Do you see that?
Yeah.
transposing simply means I took something and I laid it on its side. Okay, but laying it on its side, the technical definition for transposing, putting that T on top, is I should make every row into a column. That's what it is. Make everything that was a row, I make it into a column. So I take the first row and make it into now the new first column, and so on. Since I only had one row, I stop there and I'm done. Right? Okay, so that's what the transpose notation is. I will now go back to my presentation. Okay, so I'm going to stop sharing this. And I'm going to go back to sharing my original slides. Okay, so far so good. So now do you have a better chance of understanding what was going on here with the WT and the X?
Yes.
WT and the X. So how big is the WT and how big is the X? Did you guys hear my question?
Is the WT 1 by 2 and the X is 2 by 1?
Correct. Correct. But I didn't want that detailed answer. I just wanted to say each is of size 2, right?
Okay.
Okay, because it's just that's the bigness, right? So, okay. So, and then we're adding on a third number, which is the bias term here, right? Okay. So if I thought about my W's themselves, if I thought about the W's themselves as having a extra 1 that I attach to this arrow here, an extra 1 on it, right? If I go to this third arrow here and attach an extra 1, then I can think of my W's as having 3 numbers, right? 3 numbers. I'd have a 0.5 and a minus 0.3 and a 1. And my X's as having also 3 numbers. I'd say 2 and 5 and 1. I wouldn't keep this separate as the bias, okay? I mean, they like to keep this separate as a bias because technically it is something separate, but I'm just saying you can think about it as a dot product or a scale up or a one location convolution of 3 numbers at a time, right? Okay. Now, so I got that answer back. That's the linear part of my calculation. Then I fed it into this nonlinear step. And now I now combined everything here. This vertical bar over here in these figures is supposed to signify going through the nonlinear step. So I did my linear step here first. Then I fed that Z in through my nonlinear step here. And that gave me an answer that I'm calling A, right? I'm calling it A. And that A I'm reporting as my final answer. So you guys clear on what the steps are to get my final answer?
Yes.
Yes.
Okay, now the next idea then is that, okay, so I went through this already. I'll come back to this later on, tell you a little bit more about it later on, much later on. So now let's look at a real example. Okay, so we're going to look at an example where we've got 2 input layers, the pale blue, 3 what is called hidden layers, which is the brownish yellowish thing, and 1 dark purple as a final output, right? Okay, do you guys all see that?
Yes.
Okay, so I'm now moving to the next slide. So now the pale blue ones are called the input layer. The yellow brownish thing is the hidden layer, and the purple thing is the output layer. Okay. Now, and then it turns out your neural network can have many hidden layers. Okay, but for now we're just going to work with a simple example like this, right? Okay. So don't worry about that slide. Okay, now fully connected just means that every neuron in the layer is connected to all the neurons in the previous layer. So you can see that the brownish yellowish one is fully connected to the input layer, right? Because everybody is connected up from the previous layer. There's no missing connection. Okay, that's all fully connected. Okay, and what you now need to understand, the big deep idea now, is that the weights, the W values, are the ones where all the learning is going to go on. Okay, so you can think of add a boost. In add a boost, you selected weights. You selected weights how? In the boosting algorithm we just finished a half an hour ago, how did you select your weights?
On how many times they were right? Never mind. Don't worry about it.
Well, each team of weights, so there was like one pattern of weights that we selected at a time, right? We selected it because it was useful to complementing the team so far, right? And who did we select it from? Meaning, where was the pool of weights to select from?
The experts?
Yeah, they were all the pool of experts, right? And there were many, many, many of them because we got a different expert every time we just shifted one of the bars, right? Right? So in Add a Boost, what you're doing is you're given all of your options of weights first. You're given all your options of weights first. And you're going to select because you are going to go to that expensive selection up front. And then you lock in your selection. You said, okay, I selected you and now you're with me. You're on my team. Then I go to the next one. I pick the next team member, bring it in, lock it in. Third one, do that, okay? In neural networks, what you're going to do is you're going to actually start out with an idiotic set of weights for the W's here, right? For these W's and these W's, you're going to start with an idiotic set of weights. And then based on what you come up with at the end as your output over here, because it is a training case, in the training case, you know what you want your output to be. Because you know that for this input, I must have a certain output here. Because you don't get that the first time around, when you go through this forward calculation, you don't get that ideal output that you want. You then take the difference between the output that you do get and the ideal output that you want, and you cause your weights to change according to the amount of error that you got here, right? So the error over here will dictate how to change your weights. And you go in and you change your weights, and then you come in again the second time with the same calculation. And because you changed your weights now in a certain manner, you changed your weights in a certain manner, you should expect the gap between your answer that the calculation is giving you and what you truly want. You should expect that gap to get narrower. Then you'll do it all over again and go back again for another round. And you'll keep changing the weights each time. And the weights will get closer and closer to what they should be, so that the final answer that you get out here is exactly the answer that you always wanted. Do you all see that basic idea of how the simple neural network works? I'll be going through much more detail and much more carefully, but I just want to make sure whether or not my explanation was good enough to give you a simple idea or not. And if you're confused, now is the time to ask. Even though I'm sure that by the end of the day, your confusion will go away because we'll be doing lots of examples, but I just still want to know who is still very lost, who has kind of more or less gotten the idea that I'm going to be basically initially starting out with idiotic weights, randomly chosen stupid weights, and then I'm going to use the error that I get here between who I get out as the final number and who I should have gotten out, because I know what I should have gotten out. I know what I wanted. And that error will allow me to go back and adjust the weights on both sides of weights over here. I'll adjust them. I'll come back for a second round and I should be closer to my desired answer. Come back for a third round, I'll get closer to my desired answer. Come over to a fourth round, and so eventually the weights will do what is called, the weights will converge. They will converge to certain weights that are the stable weights that you want, and that gives you the right answer for that particular example. Is that kind of process clear?
Yes.
Yes.
Yeah.
Okay, at least at the conceptual level, right? We'll go through much more detail about how that all happens, okay? So now I'm going to take you. So in this particular case, they're saying, so here they're going to say, the concrete example they want to work on is one that says, design a binary classifier which outputs 1 if the absolute difference between the inputs is an odd number, okay? So if you started out with a 2 and a 5 as your inputs, right? Then you know that the difference between them is a 3, which is an odd number. So you want your output to be a 1. You want your final output to be a 1, okay? If on the other hand, you started with a 5 and a 3, then you know your gap between those numbers is a 2. So that's an even number, so you want your final output to be 0. So depending on which pair of numbers, whether I put this pair in here as x1 and x2, or whether I put this pair as x1 and x2, depending on which pair I use, I should expect to get either a 1 or a 0 out here, right? Is that process kind of clear? That's what I'd be trying to do?
Yes.
Okay. So now we're ready to actually go ahead and try to make it happen, right? So we will go through and we will actually calculate. We'll now use a 2 and a 9 as our inputs. 2 and a 9. So we know that the gap between the 2 and the 9 is 7. So 7 is odd, right? So 7 being odd, we're expecting our final output here to be a 1, okay? So let's go through the calculation. We have some bias terms here as well, okay? Some B's, okay, that are waiting over there. So we start with some randomly generated weights. These are the weights, 0.2, 0.6, 0.1, 0.8, 0.3, 0.7, and so on. We do all that, and we go through the first calculation, and that comes up with this number, 7.7. We feed that 7.7 into the sigmoid calculation. The sigmoid calculation was the one that looks like this, right? We feed it in, the 7.7 as the z value, we feed that in, and we get the value 0.99, okay? So we get a 0.99 out here, but we had actually wanted a 1, right? So, oh, no. We don't know that we want a 1. Sorry. Yeah. We're not there yet. We only at this answer over here, right? Okay, yeah, we're not done the last one yet, okay? So we got a 0.99 something this answer, right? Now we do the same for the second set of numbers over here, right? For the numbers coming into this thing here, we do the calculation again. We get a 0.982, and then we do a third calculation here for the numbers coming into here, and it ends up being 0.9986, right? Now these are 3 now new inputs. These are the inputs to this last step over here, with these being the weights, okay? So now we have to finish that calculation. So we do all of that. We multiply this by this, we multiply this by this, multiply this by this. We get some number, we feed that into the sigmoid, and then we finally get the final answer. We finally get the final answer now, which is a 0.8796. Okay, do you see how we got the 0.8796 answer? Hello.
Yeah.
I mean, I know I've sped through it a little bit fast, but it's all, at this point, it's all pretty what is called the forward calculation, okay? The forward calculation is pretty fast and pretty straightforward. So we go through it and we come up with that. And then what we're going to do is we're going to say what had we wanted to come out there instead of the 0.8796. What had we wanted?
A 1.
We wanted it to be a 1, right? So that difference between the 0.87 and the 1, we will then figure out how we have to adjust each of these tiny weights here. We have to figure out how to do that. And that is going to take a whole different half an hour at least. So I think this is a good time to take a break. You guys are going to take a break for an hour, is that right?
Yes.
Yeah.
Yes.
Okay, so enjoy your lunch. If there's anything that you need to review from these slides to be keeping up till this point, if you need to go back and look at something or any particular thing that I've done, even on matrices or whatever, just go and think about it carefully, but do enjoy your lunch as well. And I will come back then here in 1 hour. Does that make sense to everybody?
Yep.
Sounds good.
Yes.
Okay, so Robert, are you still here?
I'm here.
Okay, so Robert and all that?
Yes.
Yeah, in the car.
Yeah, so Lobo in the car, right? These are the 2 examples we're training on, right? So when Lobo goes through, I'm expecting my final output to be a what for Lobo?
Did you say 3?
I said 3, correct. So 3 is the good answer to give, right? Okay, 3. And on the other hand, when I come in with the input of the car, what did I say I wanted my output to be?
0.
0, right? So depending on which one I'm using, I'm going to put that target output here, and I'm going to do the back propagation, changing the weights, right? But I won't do those only once. I will do those a million times, right? A million times of the car and a million times of me. Back and forth, back and forth, back and forth. Ultimately, the network will stabilize to some weights that will correctly, when given Lobo's vector over here, will produce the number 3 or close to number 3. And when given the car pixels over here, will produce close to the number 0. And that's when the network will have stabilized. And right now, it could have done just those 2 examples. Now, in practice, nobody wants to do that only because you're not just trying to recognize Lobo versus a car, right? You're trying to do much more complicated things, okay? But that's the basic idea of how these simple neural networks work, okay? So generally, are you getting the flavor of it, guys, enough to move on?
Yes.
Yeah.
Okay, and all the people who need to answer me are answering, right?
Yes.
Very good, okay. So then I'm gonna take you now to the next set of slides.